This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Got with me Chuck Nice. Chuck, baby.
Hey, Neil.
All right.
What's happening?
So, you know what we got today?
Yeah.
We got an old favorite.
Yes, we do.
Oh, my gosh.
Someone who is, I will say, just as popular in the world of science as you.
Brian Cox.
Yes.
Welcome back, dude.
Thank you.
Yeah. So, you are professor of particle physics at the University of Manchester.
Yeah.
And that's outside of London? Where is that specifically? Or is it in Manchester?
Manchester.
It's in Manchester.
The best way I can describe it is near Liverpool, if you're that. So
Near Liverpool.
there you go.
yeah, it's roughly where the Beatles came from.
Yes,
Right that way.
yes. You've got very popular podcast, which I've been on once, maybe twice, The Infinite Monkey Cage. Yes.
BBC. I wonder whether it's a good title, actually, because it's not got science in it. So if you don't know what it is,
Right.
you have no idea what it.
And you know that
What
it's
it's gonna be,
addressing the
but-
probability of phenomena happening with an infinite
Yeah.
number. Weren't people worried that you were actually caging monkeys?
We did have some complaints because it's a BBC show. A lot, the British people are very good at complaining in letter form,
Right.
in green ink.
Absolutely.
You probably get some of that.
And that means that that this letter is going to be exceedingly unpleasant.
Yes,
Wow.
and someone did complain about it being cruel. Although we pointed out that an infinite cage is roomy.
So they were tripping on the word cage there.
Yeah,
Right.
yeah, monkey in cage.
Right.
Infinite, they missed.
And Brian, you just coming off of a tour that put you in the Guinness Book of World Records.
Oh.
That is
Yeah.
crazy fact. So,
Yeah.
so what are the details of that?
The world record, which admittedly I'm not sure how much competition there is for the biggest science tour, it went on for quite some time. It went on for about 4 years in the end. And I think the number was something, nearly 500,000 people came.
Okay.
Which was a wonderful thing for people.
Right. So it was counted as one tour because it was the same topic.
Yeah, it actually changed a lot. Because as
But it
you
had the
know,
same title.
It's another complaint we get actually on a BBC show. It's like, you scientists, you keep changing everything. You know?
Oh, yeah.
We make new discoveries. So over that 4 years, it's been remarkable.
Because you had to
actually,
stay current with the science.
Yeah,
And remind me the title of that? I actually saw that show.
That was Horizons.
Horizons,
yeah.
yes.
You saw an early version of it, I think.
Yeah. You've hosted multiple BBC shows.
Yeah.
With lofty titles, right? Like you've taken on the whole universe. The solar system.
We've done a solar system type show 3 times.
Okay.
And did struggle with the title because the first one was called Wonders of the Solar System. It was initially, by the way, going to be called 7 Wonders of the Solar System.
Oh.
There's a very famous broadcaster called David Dimbleby. I don't know if you know him here. But he's an institution. And he had something else. I think it was called Seven Wonders of the World or something like that. It was on at the same time. And people thought that there might be some confusion. So they turned in to have this wonderful history show about the development of the British state or whatever it was, like, over 1,000 years. And they get me talking about planet. They just crossed the 7 off
out.
because I was the junior person.
Okay,
So it became
all right.
Wonders of the Solar System. And then we did it again, about 10 years later and called it The Planets. And
Very
then we
simple
did it,
and direct.
And then we did it again. And then we thought, we've done Wonders of the Solar System, we've done the planet, so it got called Solar System. So we're starting to. So I don't think we can do another one just purely because
Ran out of titles.
Yeah.
Okay.
Basically.
And you also had a cosmology show, right?
Yeah, so we've done
Wonders
a
of the
few on
Universe, I
cosmology.
guess.
But it's interesting to me that usually the solar system shows do the best. And
Is there
I don't
tangibility
know why.
to the objects that are in it?
Or also people
Yeah.
know it already. They know
The moon,
about
the sun, the
moon,
planets.
sun, the
And, you know, your
planets.
first science project
It's
in
always-
elementary school is ball,
Right.
styrofoam balls that you
Yeah.
paint to mimic the planets. It's
and-
deep within us.
And someone said that to me, even when you're little, you have those things over your
Even
over
your
bed
mobile.
when you're 2. Yeah. And so maybe it's something about the planets, I think. And also it's easier to film, as you'll know, as a TV show, if you're talking about the volcanoes on Io, you can go to a volcano. Whereas if you're talking about a supermassive black hole, it's difficult
hard to
to
get there.
decide what to
Kind of hard to send a film crew.
what to point the camera at.
Yeah, so that's important sort of taproots to your visibility, your popularity, not only in the UK but worldwide. So now you're saying, all right, we got this Guinness Book of World Records record. Let's keep going.
Well, I wanted
I
to
love
do
this next topic, emergence.
Emergence, yeah.
Oh my gosh.
I really love doing the live shows and I really enjoy writing them. And the Horizon show that you mentioned earlier had been written, 5 or 6 years ago because we start developing the graphics a long time in advance. So I'd had all these ideas for a very new show, partly or actually inspired by Kepler. So Johannes Kepler. You probably know, he wrote a very beautiful little book called The Six-Cornered Snowflake, which you can get today. It's still in print. You can get it on Kindle. It was about an experience he had in 1609. He writes that it was New Year's Eve, 1609. So I think he's embellished it a bit. It's a beautiful story, though. He was walking across the Charles Bridge in Prague from the observatory to his patron's house for a party on New Year's Eve. And he realised he hadn't bought his patron a present. And then he noticed snowflakes landing on his arm. And he looked at them and he got interested in why they're all six-cornered. His book's called The Six-Cornered Snowflake. So what is the origin of this symmetry of the snowflakes? And so he went to the party and he said to his benefactor, I have brought you the gift of almost nothing, because I know how fond you are of nothing. But he said, in that gift of almost nothing, which is the snowflake, you can read the entire universe, which is a beautiful line. And so in this book, he speculates.
I got to tell you, that's the worst.
So it's a very funny book. So you get this insight into Kepler as a really witty kind of person. Yeah. So he obviously knew that.
Of course.
But the thing is, it's a very modern way of thinking, because he's saying that the symmetry of the snowflake has some cause. He says that there's a quote that's something like, I cannot believe that this symmetry, this six-cornered nature, can exist without reason. Because they're all six-cornered. So there's a reason for it. And obviously we now know it's the water molecule.
Right.
We didn't know about molecules. Yeah. Really a 20th century discovery.
Yeah. Exactly.
So he talks about beehives and pomegranate seeds. But what's
beehive with the hexagon in the beehive. Yeah.
So he says, what's that? What's the reason for that? Which again is quite complicated. And we figured out in the 20th century.
Right.
Different reasons. But for me, it's wonderful because you see this mind, this modern mind, asking a very modern question, which is, what is the origin of this symmetry that we see?
Interesting.
And so I think it's a really beautiful book. And at the end, by the way, he says, the translation I have is, I'm knocking on the doors of chemistry. Now, I don't know whether that word was around at the time. That's the translation.
Alchemy was there for sure.
So he said, I'm knocking on the doors of chemistry, but I don't know enough, so I leave it to you, dear reader, to take the next step. It's an humble, absolutely magnificent book.
Yeah.
So it would be one of many examples of emergence.
Yeah.
So, because I have a very limited list of what I know is emergent. One of them, and correct me if I'm wrong, you can study a bird all you want and know everything about it, but you would not know from that a bunch of birds will flock together.
And in syncopation, change direction all at once.
Exactly. You don't get that from studying the physiology of the bird.
Yeah.
And that's an example. That's a fine example, is it?
Yeah, emergence. I mean, even...
Well, you know what? Before we go any further, what is emergence?
Well, at an even deeper level, you could say consciousness is an emergent property. That's probably the most famous one that people discuss.
Yeah, well.
Because it's a property of some atoms and molecules in a particular configuration. We can discuss, some people don't think that, but that's the scientific view, is that's what it is. And so, but also there's this idea that it's not that there's a more fundamental description, in a sense of a better description of this complex thing, as you said, like birds flocking. There are different levels of description that are appropriate in nature. So biology, you could try to say, well, if you knew all about particle physics and a theory of everything, then you could predict, a human being. But of course you can't. So in all science, there are different appropriate levels of description. Nuclear physics would be another one. You don't do nuclear physics, at least at the moment, by doing particle physics. So I suppose emergence is, to my mind, most simply the question of how does this complexity that we see in the world emerge or appear from the simple underlying laws.
And that is layered depending upon what you're observing in terms of biology or physics or the bird.
But in the end, would you say it's just all physics?
Well, no, I think the modern view is
I'm asking a physicist that.
Of course.
Yes and no. So yes, in the sense that the complexity that we see has an origin, of course, in the laws of nature that we understand. But scientifically speaking, the correct way of, the best way of being a biologist, trying to understand complex biological systems, is not to be a particle physicist. It's a completely different discipline. So
even if you are foundational to everything that's happening, it's pretty useless at the level of the biology.
Yeah, the standard model of particle physics, there's no point in trying to understand the brain by starting with a standard model of particle physics. You will get nowhere and probably never will.
Gotcha.
All right, so you built a whole public show, stage show on this one topic.
Well, it starts with Kepler, because one of the things I like doing with live shows is developing graphics and sort of spending time working with people. So it starts on the Charles Bridge with a snowstorm, and I tell that story.
But just to be clear, this is with a video wall.
Well, yeah, by video, that's the other cool thing, because I get to, in the big shows, I believe the video wall we're going to have is 100 feet wide by 50 feet high. So it's just the biggest LED wall you can fit in an arena. So, but it starts with that, but pretty quickly we go into the snowflake and then journey inwards initially. So the modern understanding of the snowflake with the water molecule, but why is the water molecule with that particular angle? 109 and
108
degrees.
Yeah, 108 degrees.
108 degrees. So then you have the oxygen atom, the hydrogen atom.
That's the angle between the two hydrogen atoms coming off the oxygen.
Okay.
Which is the origin of the symmetry of the snowflake, ultimately. Right. And then you go to protons, and we go into the proton. I mean, my PhD was, broadly speaking, on the structure of the proton. I worked at a lab in Germany called DAISY, an accelerator called curated.
DAISY has great graphical representations of physical phenomena.
Yeah.
It's DAISY collaboration.
A very famous lab, DAISY.
Yeah.
And so we were looking at the structure of the proton, really mapping the structure of the proton. So we're going to the proton and then into quarks and quarks. So a proton made most simply as two up quarks and a down quark, which as far as we can see are point-like things. They may well not be point-like, they probably aren't, but we don't have a powerful enough microscope. So we just see this point. But then there are all sorts of other things in the proton, gluons and strange quarks and anti-strange quarks and things like that. So it gets complicated. So we zoom into that. And then we go a bit more speculative and zoom into maybe what are the building blocks of quarks? Is it superstrings? Is it string theory or something like that? So there's an element of a journey inwards and then a journey outwards again. So the show works, particularly in the second half, actually, physically with our intellectual journey. Because if you think about it, Kepler, you could say, I mean, you'll have comments on this, you could say that's the beginnings of modern science, around 1600.
Yeah, definitely. Well, this near simultaneous invention of the telescope and the microscope.
Yeah.
They came out within 10 years of each other. And we're often running in both directions once you have that.
Yeah, and it's, so, you're post-Copernicus, but Kepler's a contemporary of Galileo, pre-Newton. So in 400 years, we've gone from essentially the same view of the natural world that we had in ancient Egypt or Greece. I always think if you took an ancient Egyptian from 3000 BC and put them in Greece, about 0 AD or so, they wouldn't be too surprised. There wouldn't be much they didn't understand.
Right.
Whereas from 1600-ish, 1550, 1600, the whole modern world has developed in 400 years because we worked out how to do science, I would argue. I mean, some historians will be watching going, it's a bit more than that. But I think...
No, where science as it is now practiced took its taproots in that era. Yeah. I mean, where you have an hypothesis, you test it.
Right.
You don't just say something's true because it feels like it should be true.
Right. It has to be repeatable.
Even something so obvious as the sun goes around the earth. That's so obvious, why even test it? But you test it, right? And so this idea of testing, and we can't give short shrift to what's your institute in
the Royal Society.
The Royal Society, yes, of London. Was that what they?
We just call it the Royal Society.
Excuse me.
Of course.
Okay.
So part of the show, although we're going inwards as far as we can go, outwards as far as we can go, talking about a lot of images from the James Webb Space Telescope and things, because they're so spectacular. Vera Rubin Observatory now, so those latest images. And the problems they're raising, by the way, is an aside about the early universe and the development of early galaxies and so on. But ultimately is a thread, which is, this is a remarkable 400 years. And in the end, so the Voyager spacecraft actually starts to take quite became a character in this show, because as this thing, which is its 50th anniversary is, 2027, isn't it?
Yeah, it was 1977 they were launched,
So it's kind of as our first emissary to the stars, I suppose, as Carl Sagan would say. So there's something, I think, quite current about how we learn to acquire reliable knowledge about the world and how that has changed everybody's lives in a way that they never changed before. So you could go for 1,000 years or 2,000 years or 3,000 years. Nothing changes really. We don't discover antibiotics.
Right.
We don't discover medicine.
Right.
And then just 400 years from people like Kepler and Copernicus and Galileo, the modern world appears. And now we stand on this threshold, I think at almost a decision point. And it's our decision, what we do with this power that we have. Do we go forward to the stars following Voyager? So is Voyager the first explorer and many will follow? Or does it become some kind of museum, with the golden record? Is it the last thing that we end up sending out of our solar system? So there's an element of that, I think, just reflecting on the position we are with so much.
You're going to be bumming some people out if you take that
no, because
path.
I'm an optimist.
Oh, okay. Yeah.
But I think that we're at a stage now where the potential, the possibilities are so great, but the risks are also great. At the moment.
Part of the risk being raised or intensified is because of the technological advances and scientific advances that we have made.
Yeah.
They actually put us further at risk. So we are all at once the beneficiaries and the people harmed by our own advancements.
Yeah, I think we've talked about this before, haven't we? That it's our knowledge exceeds our wisdom. So we have power to do things like build nuclear weapons, for example, power to change the climate intentionally or unintentionally. And maybe we don't have the wisdom to control that power.
Yeah.
Bumming us out, dude.
But I'm an optimist. We've done well so far.
Right.
Yeah, we've had the power to
We've done well in
destroy
spite of
ourselves.
ourselves, really.
Yeah, we've had the power to destroy ourselves since
Several
the late
times,
1940s.
Yeah. I think, what do you feel about this? I mean, this is more philosophical, but for both of you, I think the amount of information that inundates the average person around the world now, thanks to, phones, places us in a position where there's more information available, but also more misinformation and abuse of information than ever before. So that, I think, raises the stakes in terms of us destroying ourselves.
Yeah, that's why I use the term reliable knowledge earlier. And I think that's one of the skills that all of us, our citizens, are going to have to learn, because we're awash with information, as you say. And now the trick is to try to find trusted sources. And it's not easy, clearly. And I don't necessarily blame, I don't blame individual citizens. To go back to Carl Sagan, one of my favorite books is The Demon Haunted World. And I love I think it's the first chapter where he tells the story of being in a taxi here in New York, actually, in a cab with a cab driver. He says, you're the astronomer on TV. What do you think about UFOs? What do you think about Atlantis? What do you think about and all of these things? But Carl Sagan, I think, with great wisdom, said that he didn't think, oh God, this guy, he's talking to me about Atlantis. He thought we have failed, that society has failed. This is a person with
Put the blame back on himself.
Yeah, because this is a person who's curious and interested and fascinated by the mysteries.
Right.
But the real mysteries.
Right, the ones that are truly fascinating.
Yeah, hasn't had access to them, which is a failure of education.
So it's
society.
You guys' fault.
It's really important that, because, I meet people online especially, but also just in everyday life who are sort of, we've got, this comet, when we will talk about it, the Atlas 3I comet that's going through at the moment, a fascinating thing that maybe what current estimates, maybe 7-8 billion years old. Has come from a distant star system.
Older than our solar system, which is only 4.5 billion.
Formed before the Earth formed. An unprecedented opportunity to observe material that's coming from a distant star system. And yet, you see people going, it's aliens. That's. I think this is what Carl Sagan meant. The reality of it, that this is something that formed before the Earth formed.
Right.
And is visiting our solar system and going back out into interstellar space, is more interesting than trying to say that it's some kind of completely useless. By the way, if it's an alien spaceship, it's not spending much time. It misses the Earth by, nearly 2 astronomical units.
Right.
It goes flying through the solar system, flying off again. It's been traveling for something like probably about 7 billion years or something like this. Can you imagine? We'll make a course correction and go around again. I'm sure it'll be fine. Not much will have changed in 7 billion years. It's in a hyperbolic orbit, right? It's not they don't even have the chance to come back.
Right.
But so that it's a good example, though.
Just to be clear, hyperbolic, there are like several categories of orbit. Well, it's actually 3 orbits we can speak of.
And which are they?
One would be a circle.
All right.
But nothing is in a circle because there's always something going on. So most are ellipses.
Right.
And if you keep making the ellipse bigger and bigger, there's a point where it sort of opens up to the outside and you get a parabola.
Right.
But that's a very specific form of a hyperbola.
Right.
And so hyperbola is just, it comes in and goes out and it never moves back around.
You're not going to see it again.
Right.
I mean, actually, I suppose, actually thinking about it, probably it's in a bound orbit in the galaxy.
So
I don't think
it's orbiting something, but
so
not the sun.
It's not the sun.
Right.
Yeah, it's hyperbolic to the sun.
Right.
Not to something else. But give us more examples of emergence, just so we can get in the bathtub with you here.
The one that's always talked about that we mentioned is consciousness. I think, and it's becoming very topical because, of course, AI and the potential development of artificial general intelligence, we're not there yet, but AGI, raises this question of what intelligence, what the experience of being human is. And so there are different, I think there are 2 categories of emergence people speak of. Actually, Sean Carroll, if you had him on the show, he's got about 5 in a recent paper. He's got loads of category 2A and 3B or whatever.
Okay.
But broadly speaking, people think of weak and strong emergence.
Okay.
So weak emergence is what I think virtually every scientist would, certainly a physicist would say consciousness is, which is very complicated, the most complicated emergent phenomena we know of in the universe, I would say. But it comes from the underlying laws. So you could model it with a sufficiently powerful computer. You could imagine modeling how the human brain works. I think most people would accept. There is also strong emergence, which is somehow the phenomena you see is not, you can't simulate it from the underlying laws. There's something else going on. Now, I would not subscribe to that. So I would say consciousness is interesting because it's weakly emergent. It emerges from this thing, the brain. How, we don't know.
What about the gas laws that we learn about in chemistry class?
Yeah.
That you can't derive from just looking at the movement of gas particles as individual. It's a macroscopic understanding of what's going on, highly accurate and very predictive, but I don't think you can derive them from just looking at how a molecule moves in a gas.
Well, you could in principle. That's the point. In principle, if you had a very
if you could model a bajillion particles,
If you could keep track of every single particle and then track them, then you would be able to then, in principle, determine.
Yeah, which actually goes back to what we talked about earlier, though. It'd be pointless. As you said, gases, you can understand them with pressure and volume and temperature.
Right, macroscopic objects,
so
macroscopic entities,
Why would you bother? Having a supercomputer track the motion of all and the momenta of all these things, it'd be a silly thing to do.
And does it matter if there's, I don't know how to say this properly, so I'll just ask. Does it matter if there are levels of emergence? Because when you say consciousness, animals are also conscious. There are dogs, they are clearly conscious. Chimpanzees, let's go down to monkeys. A capuchin helper monkey is definitely conscious, but it is not conscious on what we would consider the level that we are. We don't know if it's pondering its existence and all that kind of stuff. Whales are definitely dolphins. So, but does it matter that there are levels of consciousness?
No. I mean, they would just be one of those remarkable properties of atoms. Was it, again, to quote Carl Sagan again, didn't he say that a physicist is a hydrogen atom's way of learning about hydrogen atoms?
I hadn't heard it at that level. I heard humans are a way for the universe to know itself.
That's also great. I've heard you say
that's a little higher up than hydrogen atoms.
Yeah, that's cool.
That's another example. In cosmology, about 3 or 4 minutes after the Big Bang, you have 75% hydrogen, 25% helium, a bit of lithium, maybe, not much else, tiny bit of beryllium, I think. And that's it. And then you go, so there's also that story which I tell in the show of how you go from that, which we have a very good picture of, let's say 10 minutes after the Big Bang, how you then go to this 13.8 billion years later, which is stars and planets, yes, but us as well. It's a remarkable story, but it's understood in broad sweep. Yeah.
Tell me about the wetness of water. What should we be thinking about?
That's another good example of something that's appropriate to talk about liquids, and they're wet. And what does it mean to be wet? Yeah, but actually at the lower level, it's just a load of molecules, oxygen and hydrogen atoms, which don't have the property wet. So again, it would be another example. So I mean, really, I mean, you can read by the literature.
You can't point to a molecule and say that's wet.
No.
But an ensemble of them, then you can measure it and see, okay, is it wet, is it not?
Interesting.
Okay.
Yeah, so, I mean, basically, I mean, in a sense, almost everything's emergent, right? That we, I mean, clearly, you know, we observe the universe at our particular scale, so sizes of things that we can see, and we're a particular size.
Right.
And so I suppose you could argue that everything that we understand and perceive as human beings is emergent, right?
But is it really? Because doesn't emergence have to have some special characteristics that otherwise would not be if you just did the same thing over and over again? For instance, the noise that happens after the cellular division of a sperm and an egg coming together, that starts a certain kind of noise that biologists don't know what, but they know that split, 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 split. And then that keeps going until there's a person, whereas when you talk about water, like that is the connection of these, you know, this hydrogen, this oxygen. And I don't care. You just keep connecting them that way. And guess what? You're always going to get that. You're always going to get water. So is that truly emergent?
Oh.
You see what I'm saying?
Oh, so you're saying in some cases it's a precisely repeatable thing.
Yeah, exactly.
Whereas in sperm and egg, you get billions of different people.
Absolutely. And so the true nature of the emergence is in the uniqueness of those separating characteristics as opposed to something that is just repeatable.
Doesn't it come down to just how many variables you're working with?
Well, yeah, it's a really beautiful way of thinking about it. I hadn't thought about it in that way, but you could say, as Neil was just about to say, you could say, well, it's just the number of variables you have to keep track of.
Right.
I think you're right. There is something that feels very different between just wetness, as an example, a liquid.
Right.
That's an emergent behavior. But you're right that when you get to life, I mean, life is surely the most remarkable example of that. And actually, some of the work that we see, I was listening to some. There's a paper just been published. I've forgotten the name. It's from a Google research group about essentially seeing replicators, which is what we're talking about here, living things emerge, that behavior emerge just from random code. So it's a very beautiful paper. I wish I could remember the name. Maybe on the strap line here when we do this thing.
You mean in human written code?
Yeah. So you just do a very basic computing language, and essentially the concept of a Turing machine, which now I'd have to explain. But this idea that you can a computer is essentially just a tape with like characters on it, or you could have just ones and zeros on it, and something that goes along and can change those zeros into ones and ones into zeros. So it can read and write on the tape, and a few other properties. And Alan Turing back in the 1930s wrote a very famous paper which introduced the concept of a universal Turing machine. So all computers are equivalent to each other, essentially.
Oh.
And so, but there's some work been done on seeing how you can just start with no coding, really, just randomness and a couple of rules for computing, and you leave it, and over time you essentially get code written that can replicate. Oh. So you get coding sequences that can copy themselves, which is what you need.
There's an economic counterpart to this, okay?
Go ahead.
So you can go to the street corner and say, I need milk, and there's milk there. I need eggs. Eggs are there, and they'll sell you the eggs, okay? You didn't set up the shop. You didn't do anything. It's just there for you. And you can say, there must be some cosmic law that is serving my needs here and now. This must be some magic force. And then you realize it is very simple economic forces operating.
Right.
Okay. Buy it, sell it for more. Okay.
Right. The laws of supply, demand, and profit.
Yeah, exactly. And get a product someone wants. Okay. That's it. Everything else falls into place. So that would be not very many variables that lead to high complexity down the line.
Yeah. And the complexity emerges, to use that word,
right.
from really some very simple laws.
That's really cool, actually.
Think
about it.
Yeah, because I want to get rich,
right?
And so I want to find something you want, and I'm going to sell it to you,
right?
And I'm going to sell it at a profit so I can get rich,
yeah.
And an entire economy unfolds out of that.
And that emerges out of this simple transaction.
And it's interesting because it raises, and this is not my field of expertise, but it raises questions about what life is,
right?
Because you could say that life is it's about information. It's really computing. Is what life is.
Holy moly.
So it's not really, what you're saying there really is biology, the nature, the physicality that we think of as life. We think of biological systems with DNA and all those things.
Right.
But you can argue that that's not the really interesting bit. Right. That's just the way that it's realized.
That's an expression.
Really
it's an expression of the true thing, which is the
computing.
Which, if that is the case, then we have stumbled into the creation of life that will replace us. Which is, if we ever get to artificial general intelligence, and what you're saying is an emergent property of computing, which is also an expression of life, then it's only a matter of time before that particular computing becomes a life form, which, of course, will outthink us, outlive us, out-everything us.
But one of the things I've been involved in, I'm involved at a research institute called the Francis Crick Institute in London, which is the biosciences. It's a wonderful place. It's a temple to curiosity. I love the place. There's a great Nobel Prize winner called Sir Paul Nurse, who's a good friend of mine, who won the Nobel Prize for cancer research, actually by looking at yeast cells. So it's a remarkable sort of fundamental study of life. But he really pioneered the building of this institute, or inspired it in his image, which is about
Francis
curiosity.
Crick co-discovered the DNA double helix.
That's why it's called the Crick Institute.
Yeah.
But we did some podcasts called A Question of Science, actually, which are around. And we just did them at the Crick Institute and with panels of experts. And it was wonderful for me because I just chaired it and asked the questions. Mm-hmm. And it was mainly audience questions, actually. But one of them was on AI. And there was an interesting split in the panel between the neuroscientists and the computer scientists.
Really?
So the neuroscientists really felt that, for example, large language models, which is what we have at the moment, were just symbol shuffling things. And the brain is fundamentally different to that. So we are not large language models.
I kind of feel that way about them as well.
I kind of feel that way too.
It's just rearranging statistical juxtapositions of words.
Right.
And
it's seeing all the probabilities.
I don't feel like it understands anything.
Yeah.
When I interact with a large language model, it's like there's this vacuous eyes staring back at me, and there's no soul behind it.
Yeah. Well, the argument what one of the panelists gave was that imagine that you're immortal, so time doesn't matter to you. Mm-hmm. But we could be in this room if we were immortal, and someone could start putting little symbols in under the door, and if we put the right symbol out, we'd get some food. Right. So we'd soon learn what the right symbol was, and then they put 2 through the door, and we'd do the same thing, and then 3. And ultimately, if we had a huge amount of time, kind of a near infinite amount of time, we'd end up having a conversation.
Right.
And we'd do it right. But at no point would we have any clue what was going on. We'd not have any understanding at all of what we were doing.
It's a transactional exchange of simple information that itself is not anything more than just
there's no understanding.
Symbols. There's no understanding.
That's one of the points of view that were expressed. But
was that the neuroscientist?
That was a neuroscientist who said that. I think it goes back to this philosopher called Searle. I think there's an argument he made a long time ago about symbol shuffling, Searle's argument. So it's similar to that. But one of the computer scientists said, no, that irrespective of what you think about that, that's what we are. So we don't know what we are. We don't know what consciousness is. So it could be that that's all we're doing. We're really, and it's true, I suppose, at the cellular level, at the level of a neuron.
Wow,
there's no understanding.
Don't tell me that. I don't want to think. I don't want to believe that
stuff.
Now that you mention it, there are acoustic stimuli coming from your mouth, entering my ear, hitting my brain, and now I process that, and some other response comes out, and maybe I'm not conscious of anything.
No, you're just like ChatGPT.
I'm just an
information processing and response machine. Mm-hmm.
Yeah,
it's very possible.
And I think that this debate is quite live, actually, amongst people, among many people who all know what they're talking about. and there are different views, which just shows you it's complex, a complex emergent phenomenon.
That makes sense. And that is why a lot of and these aren't like neuroscientists, computer scientists, but there's many in the AI world who feel like given enough time, you just train the AI on everything. If you have enough time and enough computing power, they will definitely be truly thinking. They're like thinking the way we consider thinking.
Yeah.
Especially when you think of thinking in that way. Right.
Yeah.
So I get that there's emergence in these complex systems, but what is this talk I hear of emergence from the standard model of particle physics? What's going on there? I thought that's a pretty straightforward grid of what exists and what should exist or how they interact.
If I understand the question right, so there are quite basic things about particles that are difficult to derive from the standard model. So the standard model is, here is the quarks and up quark, down quark, electron,
It's an
neutrino.
inventory.
So we have 12 matter particles, the Higgs boson, and then 3 forces that it describes.
It's an inventory.
Yeah. And it tells us about the interactions, but it's got how particles interact with each other and through which forces do they interact.
Mm-hmm. Can I ask this? I don't care if I feel stupid or if I seem stupid. Why do you guys call them particles when it seems like everything that I read, once I go anywhere in depth, that it's more like a field of, I don't know. But you call it a particle, which makes me think like a little piece of something that's kind of floating around, and it's a tiny little, but
they always are when we observe them.
So it's really about the observation.
Well, but you're right. So the standard model of particle physics is a quantum field theory. So you're right that the objects in the standard model are fields, but maybe it's historic nomenclature. But it's true that when you always see, we detect in a particle physics detector an electron.
Okay.
And it goes to a place in the detector.
And just to be clear, you detect the signature of an electron. You don't actually see the electron.
No, we don't see it, but we see it in the...
We see its path that it makes or other things that it has touched on its way through the system.
Track that it takes.
Track.
Yeah,
right.
we have magnetic fields, and so the charged particles are deflected.
So are you seeing a disturbance in the field that shows up as this singular kind of identifier?
I think you have to say yes to that.
Yeah.
Sometimes when you guys talk, it makes... What happens is my physical association with the world kicks in, and I'm like, well, that can't be because it's not that. And so, that's why I'm asking this.
Yeah. And it's a good question about how are you to picture the existence of, solid this existence in terms of quantum fields. It's a rather abstract underlying description. So that's absolutely true.
Okay.
But you're right what you said, that they're just the particles are we'd say the excitations in the field. But
gotcha. All right. Very cool.
Can you start with the standard model and derive quantum field theory from it?
No, the standard model is a quantum field theory. So, and there are lots of what we call free parameters. So that ultimately things are put in by hand. And there are a lot of them.
Does that make the standard model that much less satisfying to you as...
It's not complete. It's certainly not complete. I mean, for example, one of the most wonderful examples is that... So how many matter particles are there in the standard model? So to make up you and me, so what's the minimal description of us? It's up quarks, down quarks, and electrons. That's it. And the up quarks and down quarks make the protons and neutrons, which sit inside the atomic nucleus, and the electrons go around to make the atoms, and that's it, right? 3 ingredients, basically. And there's another one called the electron neutrino, of which there are a lot streaming through our head now from the nuclear reactions in the sun. So the 4 things, that's it. Now, it turns out that there are also 2 copies of that set. So there's a thing called the charm quark and the strange quark, and the muon and a muon neutrino. So the muon, for example, it's a heavy electron. It's identical in every way except it's heavier. And then there's another set, the top quark and the bottom quark, and the tau neutrino. So 3 sets of these things. So the one that makes up everything, and then another 2. Why? We don't know. We don't know why there are 3 sets.
So
it's a good job
the particles of the universe are in triplicate, except we are familiar only with that lowest energy regime, with electrons and
then we discovered the other ones, and we with some very straight little caveats. We know there are no more than 3.
Why not? How do you know there are no more than 3?
Because it was so the caveats are very weak. But so at the LEP collider at CERN, throughout the 1980s, 1990s, that machine was built in the 80s. It was run through the 90s. And
did you have a position at CERN for a while?
Yeah. So I worked on as we're building the LHC, I worked on some ideas for little detectors close to the beams and so on the Atlas experiment. Before that, there was an electron-positron collider there called LEP, which was in the same tunnel. And that was really a factory to make things called Z bosons, or Z bosons, as I call them. And they're to do with one of the forces of nature, the weak force. And by measuring exactly the what's called the lifetime, the behavior, let's say, of that particle, you can see how many things it can decay into. Because basically the general rule in particle physics is if you're very massive and you can fall to bits into lighter things, then you will. And the more chance there is, the more things you can fall to bits into, the more rapidly you fall to bits, right, basically. So you can measure how many particles this thing can decay into. And so with some caveats about other generations, as we call them, being extremely heavy and you wouldn't see them, then you can see how many different kinds of particle this thing can fall into. So it's a very famous measurement. So we're sure that there are these 3 copies.
3 and only 3.
But that looks like the periodic table of the elements. Right? Mendeleev went back all those years ago. So the pattern that you can see that we all learn at school in the chemical elements, and there's an underlying reason for that, which is quantum mechanics and the way that everything works. But so there will be a reason why there are only those 3 families. There's a lot of that in the standard model. Right? There are a lot of things that we don't know. We don't fully understand the Higgs particle at all.
Okay.
We've detected this thing. It is
got the Nobel Prize given.
Yeah, and Higgs. It's a remarkable new property of nature, a new kind of thing in nature. But exactly how that works, whether and why. So we know that it gives masses to the fundamental particles, at least in the standard model, that's its job. But why it gives the masses to them, why is the electron the mass that it is? In the standard model, you say because it interacts in this way with the Higgs field, and you go, why does it do that? And we say we don't know why it does that. So there are a lot of things in the standard model that you have to measure, and so it's not a theory of everything by any sense.
And how come it doesn't contain gravity?
Well, so now you're asking about a quantum theory of gravity, and Einstein.
Up with it.
Einstein spent the last 20 or 30 years of his life trying to find such a thing. I interviewed. It was an honor actually. I interviewed Roger Penrose a few weeks ago, and chatted to him about these things. And Roger Penrose is one of the greats of the 20th and 21st century. He got the Nobel Prize for his work on black holes, for really a very famous paper from 1963, I think it was.
66?
Was it 60s?
Yeah, 60s, mid-60s, yeah.
Where he showed that with very minimal assumptions, a sufficiently massive star will collapse to form a space-time singularity, a black hole. So,
inevitably.
Yeah, inevitably. So Oppenheimer and Schneider did it in just before the Second World War, but with some assumptions about symmetry. And you could say, well, nothing collapses in a perfectly symmetric way, so you wouldn't form a black hole. But Penrose removed those ideas. But he's a great relativist. He's a great, a real expert in general relativity. So he would not, I suppose the fashionable way to think about this is general relativity comes from quantum mechanics, but we don't know how. Wow. And there's some support for that from the study of black holes a bit. But there is another way of thinking that says, no, space-time is fundamental. Relativity is fundamental. I'm saying that because there's debate. It's not. I think most physicists would say quantum mechanics is the underlying theory, some kind of quantum description of nature.
It's on a roll.
And out of that emerges.
It's on a roll for how successful it has been.
Yeah.
In accounting for everything.
Yeah.
Right. I mean, so why doubt it at this point?
Yeah. So maybe we don't know enough to start I think I'm not misrepresenting him. He would question whether you really need to have a quantum theory of gravity coming from quantum mechanics. I think he would question that. So the reason I'm saying that is to say it's an open question. We don't know. So
what about the fabric of space-time? Ooh. Is that emergent?
Well, so the recent work in the study of black holes, which is the tiny bit of research I still do. I had a PhD student and postdoc working on this. It's called emergent space-time.
What is that?
So it's the idea that space and time are not fundamental. So space-time is not fundamental. There's let's say a deeper description, which is basically a network of qubits, to do the shorthand version. So qubits, quantum bits. So essentially it looks like a quantum computer. Absolutely not to say that we live in a simulation. Right? No one's going.
He's a little defensive there. Have you noticed that? He sounded. I don't really mean that.
I don't know whether we live in a simulation. Nobody does, but I'm just saying it's not evidence for that.
Right.
But it's beginning to look like you can say, well, let's say a notion of distance can emerge from a network, an underlying network, which doesn't have the notion of distance or geometry in it. So
you just described subspace from Star Trek. It's like this underlying substrate where the laws of physics aren't necessarily in play, which is why you can go faster than the speed of light.
Well, information goes faster.
Goes faster.
They communicate in subspace with witty repartee.
Exactly.
Even though they're
half a galaxy apart.
Right.
Yeah.
Right.
It's interesting. I was thinking about this in another context, actually, because so there would be laws of physics, by the way. There'd be underlying laws.
Right.
And then our laws would emerge from them.
Please forgive my inelegant description.
We call them effective theories, right? So it's an effective theory,
right?
Which works in the regimes we observe things. But
effective theory.
But I was thinking about this, and I have no evidence for this at all. So I might cause lots of people to write in. But I think that causality, for example, cause and effect, which is what you're saying if things can go faster than light, then you can essentially build a time machine and go into the past. You can send messages back into the past if you can go faster than the speed of light, basically. My guess is that that's absolutely fundamental. And so you wouldn't, just because you can skip, if you could skip beneath relativity, so to a deeper picture of space-time, I still guess that causality will be there.
Will still be there.
I'm not aware of anyone who's proved that, or I'm not aware of anyone's opinion on it. It is my opinion.
Yeah.
I don't think I have any evidence for that other than Stephen Hawking.
How is that different from Stephen Hawking's time travel conjecture?
Yeah, the chronology protection conjecture.
Sorry.
So it's called a conjecture because he conjectured it.
It was conjecture.
And that was his conjecture, you're right. He said that whatever the underlying laws of physics are, they will prevent time travel into the past, which is to say that causality
protecting
is
causality.
Right, exactly.
But I think we're absolutely miles away. We're miles away. This might not be right, this idea of space-time emerging, although it's quite a popular research field. Mm-hmm. It is interesting because quantum mechanics can seem to violate the spirit of that. So you probably discussed before on the show quantum entanglement.
Yeah. Everybody wants to know about quantum entanglement.
Einstein called it spooky action at a distance, he called it, right? So he didn't like the idea that you can have these widely separated things that can appear to be correlated in such a way that something happens instantly. Now, we know, John Bell and others showed, and it's been experimentally tested, that information can't travel faster than the speed of light.
Right.
But still, the idea that some kind of, call it configuration, that the quantum state can change instantly, seems to violate that somehow, doesn't it? So this is, again,
I heard from
research.
The other Brian. I was having lunch with him, and he said something that just blew my mind. What might be fundamental in space-time is this sea of entangled virtual particles where the particles are entangled via what are essentially wormholes.
Yeah.
Because a wormhole has instantaneous contact from one side to the other. And the wormholes then are the stitching of the fabric of space-time.
It's called ER equals EPR. which is Einstein-Rosen equals Einstein-Podolsky-Rosen. So EPR is the spooky action at a distance paper, and ER is Einstein-Rosen, which is 1935, I think, where they showed that the Schwarzschild metric, the eternal Schwarzschild metric, which is the description of a non-spinning black hole, which was discovered very early in relativity, has in it, if you extend it as far as you can, a wormhole geometry. So that was Einstein and Rosen. So it's called, I think Leonard Susskind coined the term ER equals EPR.
So what does that mean to you as a thinker in this space? Can wormholes be the fabric of anything?
Yeah, it's part of the answer. One of the answers for how information might get out of a black hole. So it's what it's called the black hole information paradox.
Okay, that's very cool. Go ahead.
Yeah. Mm-hmm. Well, one of the pictures people have for that, very hand-wavy picture, is that wormholes somehow connect the interior of the black hole to the external universe.
But all the other virtual particles that fill the vacuum of space, those are particle pairs that come in and out of existence.
Yeah, they're entangled.
Why wouldn't they be? They're entangled. Why wouldn't that also be in this wormhole discussion?
Yeah. Yeah, exactly.
Okay.
So that's it. So it seems there's some sense of a link. The reason it came in the black hole context is people did very complicated mathematical calculations about what happens to the Hawking radiation. So this is the radiation that is emitted from a black hole. And it's really, one way to think about it is it's the event horizon of a black hole is disrupting these particles that you talked about, these entangled particles that are really the structure of the vacuum of space, right? And it kind of disrupts them. And so people were calculating how that radiation, which is entangled with the black hole, how everything behaves as the black hole shrinks. Because if you think about it, this black hole is glowing, it has a temperature, losing energy
through Hawking radiation.
Through the Hawking radiation. So not at the moment, because they're much colder than the cosmic microwave background. So they're cold things at the moment. But eventually in the universe, there'll be hot things, and they'll shrink.
It'll be hotter than the background. So there'll be net flow of energy is out.
Yeah, but eventually they'll shrink. They're entangled with the Hawking radiation because of what you said, because of these pairs that are coming out of the vacuum. And so you get to a point where you get a crisis, really, where the entanglement can't be supported. It's one way of thinking about one of the problems with the black hole information paradox. So it's all to do with entanglement and what happens. And so from that research, some calculations were done, which are just mathematical, that say that ultimately the Hawking radiation ends up essentially entangled with itself again. Right? It's one way to think about it. Because... So you don't lose information. But those calculations can be pictured with hand waving as representing wormholes, some sort of wormholes. They're not the Einstein-Rosen wormholes, actually. So it gets very complicated. And people aren't clear on the interpretation. But that's where the modern resurgence in this idea has come from, I think. It's coming from these really very technical calculations about black holes and how information behaves in the presence of black holes. And wormhole-like structures appear to be one interpretation of what's happening. But I'm choosing my words carefully because it really isn't fully fleshed out by a long way. Yeah. It's interesting, isn't it?
But it is really fascinating to think about. This is how it's like an information tunnel just for that, for the purposes of getting it out.
Yeah.
So,
and then you go, why? And even, you see the language. It's like for the purposes of why is it that information is conserved? Right. That looks quite basic. So it looks like another of these basic ideas. Information is not destroyed.
Right.
It becomes massively scrambled, so you can't in any conceivable future read the stuff. But it's the example that's often given is if you burn, but it's the iPad. Let's say you set fire to the iPad. You might say, well, surely I destroy the memory. But the idea is that you don't, if you could measure everything that came off somehow, all the photons and everything, the whole thing, then in there, scrambled up, you could reconstruct.
The iPad, even though you set it on fire and all those atoms, and every particle that was in there, if you could get them all together, you would be able to say, oh, that was the iPad.
Yeah, and you'd have your photos in there, whatever it is. You could, in very principle, but really in principle, not practice, reconstruct. So you don't destroy information.
Yeah, you don't destroy information.
It's also determinism. It's called unitary evolution in our language, right?
Really?
You don't destroy information.
Gotcha. So that energy and information, conservation of energy, conservation of information. Can we think about them like that, or is it not? Is that a wrong way to think about it?
It's less about information, more about entropy, right? I mean, entropy, you can move from one place to another, and then you can measure that or think about it as an entity. Whereas,
I get that.
A point we were raising before, obviously if I send a molecule that has structure, a DNA molecule, into a black hole, and it gets ripped apart, and then it comes out as separate atoms, I lost all that DNA information. However, that DNA became DNA at the expense of the sun or whatever other input of energy.
The energy that went into it.
That's correct.
Gotcha.
Right. So you draw a sphere around all the action. So then you could talk about sort of entropy moving,
right?
Without having to inventory the shape of the DNA molecule.
Right. Because the DNA molecule is a result of the
energy. It was taking energy from another system.
From another source that put it in that made
Correct.
that.
Yeah.
Oh, wow.
Yeah.
Okay.
It's so fascinating that this work on black holes, black hole information paradox, emergent space-time.
Yes.
But it's such a early stage that I don't think there are popular articles that really, the language isn't there yet. It's just mathematically difficult.
Yeah. Wow, man.
So we're doubling up on this and adding a whole segment of Cosmic Queries, which is a branch of what we do here. It's beyond just conversations. People get to ask questions, and we tell them who the guest is going to be, and they direct questions to that guest. You have been duly outed on our pages, and you have a whole fan base out there, and they're eager and dying to hear from you. And we have some professional overlap, but in the questions that'll come in, it's not likely that I will ever need to jump in. And I look forward to basking in your brilliance in the face of these questions. All right, quarks. You've never had an isolated quark?
No.
Okay, so as you pull two quarks apart, you're actually putting energy into the system by doing so, like pulling a rubber band apart. And at the point where the quark connection breaks, there's enough energy you just put in so whole new quarks are created. So now you have two pairs of quarks.
Yeah.
I might be simplifying it, but that's the idea.
Yeah, basically. We call it hadronization.
Hadronization.
In particle physics.
Okay.
Yeah. And we have models of it.
Okay, gotcha. So now watch. I now have a quark pair falling into a black hole. It's nearing the singularity. Tidal forces stretch it, putting energy into it. It splits, makes two pairs of quarks, and they keep falling in. Will this create a quark catastrophe? Because the tidal force will continue to split the quarks and make a new pair of quarks. Will the singularity be overridden with quarks that were created from the tidal separation and the formation of brand new quarks in the energy that was invested in it? Am I taking energy out of the black hole by making quarks with it? What's going on there? And I'd rather think of it I want to think of it as a quark catastrophe because that's way more fun.
I mean, you're not taking energy out of the black hole because all this is happening inside the horizon. For a big black hole, anyway, I mean, I suppose you could say for a micro black hole,
where the separation is on the same scale of that.
But
okay, but why don't I just make a bajillion quarks as it falls towards the?
I've never thought of it before. It's a beautiful picture.
Yes,
because clearly you'll do that. You rip matter apart. That's the way it's usually said. Mm-hmm. So people just say matter, everything gets ripped apart. Even the protons and neutrons and even the quarks get ripped apart when you go to the singularity.
But to rip apart a quark has consequences.
Yeah, and we don't know what the singularity is. I mean, other than it looks like a moment in time. It looks like the end of time, which we've discussed before, I think, which is also a difficult thing to think about. So there's a finite amount of time in there for the quarks themselves when they're inside the.
That's a way out
of that.
But
or wait, just to be clear, wait, was that what Penrose said? Because as you cross the event horizon, what was previously in front of you in space is now in front of you in time.
Yeah.
Because we had Jan 11 here. She's our resident, up the street cosmologist. Yeah. So the time in front of you is finite. So it can't keep splitting quarks forever and creating.
No, you don't have forever. I mean, even off the top of my head, even the big black hole, like the M87 black hole, which is the one we have a photograph of.
Yeah, the one that had all the ones that made the news.
6 billion solar masses or something like that thing. Yeah. And in there, I think you have about a day, it's about 24 hours or so, if you cross the horizon before you go to the end of time. Wow. It's roughly speaking a day, give or take a factor of 2. I can't remember exactly what it is, but it's something like that. I mean, it's one of the fundamental properties of general relativity.
Why can't I notice it?
Well, you wouldn't notice until the tidal forces became important.
Right.
Which is what you're referring to.
Then I get ripped apart.
Right.
Yeah, so when you cross the horizon, so this room, we could be falling across the horizon in Einstein's picture, purely in Einstein's picture, we could be falling across the horizon of a supermassive black hole, would not notice.
Right.
So from our perspective, everything's normal. Ultimately, you'd feel the tidal forces. But
as you get closer to this singularity.
I think it's within the last few seconds for these, if I remember rightly, for the very big black holes. And then you feel it. And then it's tidal forces, but you wouldn't have time to react, really. You just go, that's a bit...
Right, but so you're not going to make an infinite number of quarks.
No, you won't make an infinite number of quarks.
Because time stops it.
Right.
I think that's probably,
get to the end of time.
Having never thought about it, that's probably the answer. You couldn't make an infinite number of massive
Maybe
things.
Maybe it could evaporate the black hole.
So you'd be
It could turn the whole black hole into quarks.
Well...
Because it's pulling energy out of the...
Well, no, the mass of the black hole will stay the same. So that process of hadronization...
I get that the mass will stay the same, but that mass energy budget is slowly getting converted into quarks because the quarks will keep making new quarks because you keep trying to rip them apart with your tidal forces.
So you're saying that space-time would unwarp because the energy...
will be completely converted into
matter.
And you have one giant quark. The quark catastrophe.
That's not what happens, isn't it? It's a brilliant question because we see black holes.
Oh, okay.
So they haven't, the geometry is not unfolded.
Then. So then you're left answering why it did not happen.
Right.
That's what
I think I suspect the answer is because of the finite time you have in there.
That's so cool.
It's also important to say that we don't know what the singularity is.
Right.
So we really...
Yeah. And we can't calculate with it or anything.
Because you can't get inside a black hole to see what it is. So Raul starts us off, Raul. And he says, hello, Lord Nice, Dr. Tyson, Professor Cox. I'm Raul, a new Patreon member from a couple streets north of where you guys are right now on Central Park. I wanted to know if there was any discourse on whether dark matter and dark energy, affectionately dubbed as Fred and Wilma by Dr. Tyson, are emergent phenomena resulting from the curved manifold of space-time. In the case of dark energy, could it be that geometry of space allows for peaks and troughs for the accelerated expansion of space, and we just happen to be observing the expansion phase? Thanks for all that you continue to do for science.
I have to explain Fred and Wilma here before we begin.
Okay.
So I've had taken issue with the terms we have invoked to describe dark energy and dark matter because it implies that it's energy and matter. And I said, what we know is that it's dark gravity. That is what it is. We don't know if it's matter. Maybe it is, probably it is, but we don't know.
Yeah.
And dark energy, is it energy? We don't know.
Yeah.
So I said we should just call them Fred and Wilma.
Yeah.
Okay? And that way there's no bias associated with the label.
There are different, so dark energy, so as you said, observationally, and we already mentioned Brian Schmitz, who was one of the people who discovered that the universe is accelerating. There is, in Einstein's theory of general relativity, a thing called the cosmological constant, which you can just put in and it does that job. But whether that's what we're seeing is a good question, and we don't know the answer. So it could be that you're seeing some kind of quantum field, which we talked about earlier. So, for example, inflation, which is the idea that before the universe was hot and dense, so before what we call the hot Big Bang, then space was stretching extremely fast, driven by something which we call the inflaton field, which is one of these quantum fields we talk about. And then that field changes and decays away. That's the end of inflation and the heating up of the universe, which we call the hot Big Bang. So it could be that dark energy is something like that. So it's some kind of quantum field that's doing it. That may mean that it changes, and it could change over time. And indeed,
so it could go away.
So it could go away. And I think that there's in the current data, which is associated with the early universe, there's a tension in between the things we measure, like the Hubble parameter and things like that, from the early universe, from the cosmic microwave background radiation, and the measurements from the later universe, which is from seeing supernova explosions and so on, seeing the expansion of the universe that way. And there are some sort of almost, probably not hand wavy, but preliminary ideas that you could be seeing that something was present in the early universe that is not present now, or vice versa. So something's changed. So it is true that inflation would be an example, if it's correct, of one of those quantum fields which then changes and goes away. And that's associated with what we used to call the origin of the universe, right? Wow. So it could be that dark energy is something like that. And also, actually, to add to that mystery, there's the Higgs field. So the Higgs field is what's called a scalar field, which is technical jargon, but it's of the same type of thing that we think the inflaton field is, and possibly the dark energy is. So but the Higgs field doesn't appear to cause the universe. Well, it does not cause the universe to accelerate in its expansion, or at least not in the way that we would expect. We'd expect it to blow the universe apart, and it doesn't. So there's something in there. Many of my colleagues think that associated with these things called scalar fields and the way they interact.
Is that something that's going to pop out of a future run of the Large Hadron Collider?
No, I don't think so. I think it's more theoretical advances that but precision measurements of the way the universe is expanding and has expanded, the expansion history of the universe. But these things are all encoded in there somewhere. So I think it's that. So the answer is to the question is we don't have a model. We don't have we have lots of models of what dark energy might be, but none of them are agreed upon or more convincing than the other. Right? We don't have enough measurement, I think, precision measurement. So it's a very good question. And the same with dark matter. Dark matter, we do have more evidence that it's some kind of particle. And some of that comes from, so I mentioned it, the cosmic microwave background. I should say what it is. It's the afterglow of the Big Bang. It's often described the oldest light in the universe. So they're photons emitted about 380,000 years after the Big Bang, which we can detect. So it is a measurement. There's a satellite called Planck that made the highest resolution pictures of this that we have at the moment. And so in there, you can model the way that image looks. It's actually sound waves moving through the universe before 380,000 years after the Big Bang. So what you're seeing is sound waves in the plasma that was the early universe. And we can
We're seeing an imprint of those sound waves at that time.
So we're seeing the imprint when the light got released, when the plasma went away. But so these are sound waves. But we have a very good measurement. We have that photograph, which shows us there is the information about the sound waves. And that allows us to model what the plasma is and what's in it. And the dark matter is a very important component of modeling the way those sound waves behave. So it's not, it's often presented as something that people invented because they don't understand how galaxies rotate or interact or something like that.
That's a real thing.
But you can see it in many different ways. So it is true that the way that our theories of galaxy formation require it, there's a thing called the cosmic web that you probably talked about before. But there's also independent measurements from the sound waves in the plasma of the young universe, and that requires them. And you can do, actually my postdoc actually did it for, it's one of the things that's in the show, not that I'm always plugging these tickets for the new show, but one of the things I do in the show is my postdoc developed a real-time calculation tool of the way the sound waves work in the plasma. And what's cool about it is you can sit there with an iPad on stage and you can just go, I'll change the recipe. I'll make the dark matter go to like 15% rather than 25% or whatever it is. You know, like play around with those things. And when you do that, the data goes completely, it doesn't match the data. The prediction drifts completely from what we see in the data. So it's highly sensitive.
Wow.
It's a beautiful demonstration of how accurate astrophysics is now, how accurate cosmology is. So yeah, I would be very surprised if dark matter isn't some kind of particle itself, because there's multiple different independent observations that suggest it is. Dark energy, we don't have precision, the precision, I think, to discriminate between the models.
Donita Bukait or Bushite, one or the other. And she says, hey, Neil, Brian, Chuck, Donita from Southern Utah. Help! I need visuals. How does the curvature of space-time cause tides? I've read explanations, but since I think in pictures, I need some visual support on this.
So imagine the Earth, and if you try to explain the tides in the ocean by just having a static picture of the Earth and the Moon just standing
still. As is drawn in textbooks.
As is drawn in textbooks. Then it's hard to figure out what's happening, because as Richard Feynman said in the Feynman lectures, if everything's just standing still, if the Moon and the Earth are just standing still, they'll just be pulled towards each other and squash into each
magnets,
other.
Like when you set them down on a table and they come together.
So, of course, the reason they don't do that is because they're in orbit around their common center of mass. So they're orbiting. And actually, you need to know that the Earth is actually orbiting around the center of mass of the Earth-Moon system, as is the Moon, in order to fully explain the tides. And so you get a good explanation. So there are centrifugal forces at work as well, because you're in this frame of reference that's spinning around and so on. So it's actually relatively easy to describe, but not as easy as it's presented on television usually.
So, and you got into an argument with the producer on this.
Yeah, so I said I can't do it without talking about the fact that when there's a centrifugal forces. It's basically because the centrifugal force exceeds the gravitational pull of the Moon on one side of the Earth, and is smaller than it on the other one. It's that kind of effect, but it's beautifully described in the Feynman lectures, which are freely available online.
Is that right?
You can
online
get them.
now.
I think they're free.
Cool. I spent real money on mine.
Well, the books
I have
you have to
hardcover.
get.
I have hardcover. I got them in the. When did I get them?
They're beautiful.
In 1981, I bought them.
Yeah.
Okay.
But it's in there. You can download. I think they're freely available now.
And there's 3 volumes, right? So classical mechanics, E&M, and then quantum.
Yeah, and it's in volume 1.
Very nice.
It's really lovely explanation of it.
So there you have it, Donita. And also you can check out the explainer that Neil did on tidal bulges. That might help you too, because it's really
I forgot
good.
about that.
It's correct.
You remember all of our explainers.
Why do you think I do this job? This is Alyssa Feldhaus. Alyssa from Tucson, Arizona here. Question for Dr. Tyson and Dr. Cox. Do you think the concept of a particle will still be meaningful once we fully unify quantum mechanics and gravity, or will it vanish like the idea of a phlogiston did in chemistry?
No, it'll be meaningful. We've been talking about emergence a lot. So different levels of description. So yes, it may well be that there's a theory of nature that we have it, right? It's quantum field theory, that just quantum fields. And there may be a deeper level in terms of qubits or whatever those things are, Planck scale things. But there will always be a level of description that where particles are the right thing. And think about an old-fashioned TV, a cathode ray tube, where you have a beam of electrons, and the beam of electrons goes through a magnetic field, and it jiggles the beam around, and you get the picture on the TV. There's never going to be a better description of that than a beam of electrons.
Right.
So maybe a deeper part of that question is, if we come to understand that everything is strings, then we don't need the language of particles. Once again, is it just a convenience?
You will need the language of particles to explain things that are happening in this room, these energies and temperatures. Because
that's how it manifests.
Yeah, it's just pointless. You wouldn't talk about these phenomena that only become important for your description of the world at energies that, trillions of a second after the Big Bang.
Okay.
I mean, just to say quarks, right? Quarks are not that you don't need those to describe nuclear physics. You want protons and neutrons.
Right.
Those are the things that you need.
And
so the quarks are hidden inside You don't feel that them. You don't perceive them. That's why we didn't discover them until 1968. I think.
Yeah. It was pretty late. You were on our way to the moon, and we don't yet know that quarks are real. Yeah,
that's wild.
Yeah.
Anyway, he says, "Hello, Dr. Cox. I've been a fan forever.
All right,
Dr. Tyson and Dr. Tice, you guys are awesome. Anyway, how do particles know it's time to decay?
Love that question.
That's a great question.
Yeah.
Sorry about your name, David, because since you asked such a great question.
So what's the best way of describing that? Is time. So they have a lifetime, which is, as I said before, is to do with, can you decay into something lighter? So there might be a reason you can't, right? Because things are like electric charge, for example. Electric charge is conserved. So you can't take a positive charge thing and have it decay into a lighter, negatively charged thing, because you'd be inventing. You can't destroy and create electric charge. You have to do it in pairs. It's conserved. A very important example is the neutron and the proton. So the neutron is a bit heavier than the proton. So the neutron can change into a proton.
And does.
And does in about 10 minutes.
Yeah.
Oh, so,
I thought it was even quicker than like 6 minutes.
Is it or 8 minutes?
Yeah. It's like you can count it out and watch
it happen.
Yeah. If it's sat on its own, it'll do that, and to conserve charge, there'll be a positive thing will go as well, and so basically it can do it. So, and the lifetime is really proportional to the difference in mass between the neutron and the proton, which is very tiny. So if it was really big, if it was much heavier, it'd decay quicker. So you've got there's the mass difference, and then there's the number of things you can decay into, the number of ways you can do it.
Yeah, but that's just a statistical average. The decay time. That's the half-life.
Yes, half-life.
Okay, so we fill out the time with some of them are decaying sooner or longer. So it's not just as simple as you described, where how much difference is there in the energy of the mass of what it is and what it can be, because there's a variation in there. I interpret that question as, how do you get that variation?
Oh, well, that's quantum mechanics. You're right. It's a very deep question.
Yeah.
It's like, and that bothered immensely the early founders of quantum mechanics. So people like Rutherford and those people who Niels Bohr and all those people, and Einstein, it bothered a lot. God does not play dice with the universe. That's essentially what you're saying. You're saying, why does God play dice, as Einstein put it?
I realized just while you were speaking that you did answer her question precisely, because she said, because why does some take longer than others?
Yeah.
And the difference in how many options it has coming out the other side.
Yeah, and the mass difference.
So that'll say why one will decay in 5 minutes or 10 hours. You can get that.
Yeah.
Okay. Given that, what is going on at the instant that it decays?
It's another
because
question.
Does that give me insight into why some will decay sooner and some will decay later, so that it averages out to that half-life?
So what's going on? So you can. It's called the weak nuclear force that's changing these things. So that's part of the standard model. So what actually happens when a neutron turns into a proton? So a down quark turns into an up quark. So what happens is the down quark, you can think of it as emitting a particle, a force carrying particle comes off. It's a W minus, which then goes to an electron and a thing called an anti-electron neutrino, actually. But it goes, so the W minus goes off, and then you get a down quark, which is a charge plus 2/3.
Okay.
So you get a minus 1/3 quark going to a plus 2/3 quark, and then you get an electron that comes off. So all the charges are conserved.
Gotcha.
So you haven't invented electric charge.
You have right.
And
so
also
the sum of all the charges at the end is the same. As
we
the
got
sum
it.
of
And when we think of a neutron decaying to a proton, all that's the engine process going on. That's the gearing that's happening that you just described.
So it's the same kind of picture as why does an electron bounce off another electron? So we'd say, well, because they've got negative charge and negative charges repel. But the particle physics picture of that is that a photon is exchanged between the electrons. So in this case, it's not the electromagnetic force, it's called the weak nuclear force. Basically, the down quark is changing into an up quark with ultimately the emission of an electron and a neutrino, and the W minus is the particle.
And in the end, when that happens, it's statistical. Wow. We got to deal with that. Are we hiding our awareness of objective reality by dusting it into the bin of probability?
No, it's not the same. That randomness is not the same as the randomness because we don't know everything. So in terms of a gas, let's say, there are things are jiggling around. We don't keep track. We spoke about it earlier. We don't keep track of the billions of molecules in the gas. So there's some statistics comes in because we're averaging over a load. The quantum mechanics is not like that. As far as we can tell, the statistical nature of it is inherently, it's built into the theory, it's built into nature.
That's
and
wild.
that bothered everybody.
So Einstein was just wrong.
Yes. Yeah.
Well, it is true that how to interpret that. Then it's a whole other episode, right? So you've probably talked to people about the many worlds interpretation of quantum mechanics. Now, that's all. That's this thing. That's all in this. How do you interpret those statistical predictions
without
the collapse of the wave function,
without invoking a statistical description?
Yeah, I mean, so it seems that it's a fundamental part of the theory.
You know my favorite part of particle decay?
What's that?
If you accelerate them,
right,
then they take longer to decay.
That makes sense.
Because Einstein's special theory of relativity.
That's
so badass.
Going closer to the speed of light, so time literally is slowing down.
And so it takes longer to decay.
Yeah.
That's a beautiful thing.
That's very cool, man.
Yeah.
Wow. All right, here we go. This is John. He says, hello, Lord Nice and Dr. Tyson, Dr. Cox. John from Arkansas here. You've both explained what a Planck length is and how we will likely never get more accurate measurements beyond this supposed limit. I am wondering if light can have a wavelength that small, and if energy would be measurable, or could that be another infinity we need new physics to explain, much like the singularity in a black hole?
I love this question.
Yeah.
I would not have been able to answer this question.
The answer is that so the smaller you make the wavelength of a photon, the higher the energy is.
Yes.
So
there should be an energy associated with the wavelength that is a Planck length.
Yes. And you find out that that energy density makes a black hole. Think about it. The more you try to probe smaller, and then the black hole would. I think Leonard Susskind calls it the UV-IR connection. I think that's what he calls it. So the upshot is that if you try to put more and more energy into a smaller and smaller space to see smaller things, the size of the black hole you make increases. It grows.
That's wild.
So the more you try to see smaller things, the less you can see the small things, right. Because the black hole gets
the universe
bigger.
is diabolical.
Yes.
Yeah. So it stops you. So you can't probe it.
Okay. And just remind us briefly about a Planck length. Just put that on the map here.
So you can construct units, fundamental units from things from specifically the speed of light, the strength of gravity, and Planck's constant. So if you take those things and put them together, so you get meters out, you'll get the Planck length. So it's Planck who figured out that it would be good to make units of measurement out of things on which everyone would agree. If you meet an alien, for example, then there's no point in talking about a meter, because what is it? It's the length of your arm or something like that.
Oh, no, it's 1/10 the length of a quarter of the Earth from the North Pole to the equator through the Paris Observatory. That's why the circumference of the Earth is 40 million meters, which is, and make that kilometers, it's 40,000 kilometers.
Right, so
is the circumference. That's why it's that even.
Yeah.
It's the French did that. But you're Brits, so you don't care what they did.
Yeah, so they're all arbitrary things that are to do with our planet or our bodies or whatever it is.
Yeah.
But then you could say, well, but the speed of light, Planck's constant, and the strength of gravity, everyone would agree on.
Even aliens.
So
yes.
yeah, because you can measure those. So whatever units you measure them in, you can put them together to make something that looks like a length.
Gotcha.
And that's the Planck length. And it happens to be very, very tiny relative to us.
Right.
Very cool.
So can there be a fabric of space-time that, in other words, if you were to quantize general relativity, you would have to, the Planck length would be fundamental to that. Is that not right?
Yeah. So we think that's telling us something deep about the universe itself.
Okay.
So these are properties of the universe. These things.
Mm-hmm.
That's the thing, not properties of planets or
Right. Exactly. All right.
Very, very cool. And Big Stu says, "Hey, what it do? My name is Big Stu from Austin, Texas.
All right.
I've heard Dr. Cox talk about how information that falls into a black hole might not actually be lost. But what is that information exactly? Does Hawking radiation somehow contain the same atoms that went in, or does the universe just eject some cosmic thumb drive full of data?"
Cosmic thumb drive full of data. Yes.
Yeah.
So the idea is that the Hawking radiation ends up. Yes, the description that who was asked the question?
Stu.
That Stu said is basically right. So in more technical terms, you end up with this Hawking radiation. You'd have to collect it and do some operations on it with a quantum computer to kind of extract the information. So it's all, no one's ever going to do it. It's impossible to do in practice. But that's the idea. In a very fundamental sense, it's in there. In the same way that I suppose the information, if you were to, I suppose, ask the question, how is the information from this photograph I took with my phone encoded in the memory of the phone? It's quite complicated, actually, and it's got error correction in it and all sorts of things like that. And it's that idea, really, but at a quantum mechanical level. So,
cool.
Yeah. So it's not physically the physical stuff, but it's the data.
Cool. Does Newton's third law hold true in quantum mechanics? Wayne from Northridge, California.
To every action, there is an equal and opposite reaction. Yeah.
Allow me to broaden it. So quantum physics and relativity has shown that the applicability of Newton's laws has limits. F is not always ma in that simple form. You need Einsteinian extensions on these constructs.
Yeah.
So even with his gravity equation, you have to modify it. And it was hard-earned to learn that Newton's laws fail. So does every action is an equal and opposite reaction have a point of failure where we need a deeper understanding or an updated understanding of how the universe works?
No. So for example, it's easier to explain the first law, everything continues in its state of rest or uniform motion in a straight line unless acted upon by a force. That is to do with the symmetries of space-time, right? So that is true in relativity as well. So if you're talking about special relativity, and it's one of the examples we teach actually in our first year undergraduate course, you can show that if something's traveling in a straight line in one frame of reference, it's traveling in a straight line in a different frame of reference under both Galilean transformations, which are the Newtonian picture, and Lorentz transformations, which are the special relativistic picture.
Both of them. Okay. Very good.
So you could actually phrase that as one of Einstein's postulates, because Einstein's two postulates from which special relativity emerges are the speed of light's a constant for all observers, and the laws of nature take the same form in all inertial frames of reference. Newton's law that says that something's going in a straight line, unless acted upon by a force, it'll still carry on going in a straight line, is one of those laws. I mean, if you think about the consequences, otherwise you'd be able to change between different points of view moving at the same speed relative to each other. And something that was going along in a straight line, according to one person, would be doing that. Would be in orbit or something.
We're intact
built
there.
in. So they're a representation of ultimately of the, and there's a very deep question as to why is that the case? And I remember again Feynman, who we mentioned earlier, talking about it. Why is that the case? And he said it's because it's one of the fundamental properties of our universe. So we don't know why that's the case.
It just is.
That is the way our universe is built. It's to do with the posh way or whatever the fancy way of saying it is the symmetries of space-time. But it's just, that's one of the fundamental properties of our universe.
Let's get some of your biography out there for stateside people who might not fully know who you are. You cut your teeth as a particle physicist. Is that correct?
Yeah, initially. I mean, actually, my degree is at the University of Manchester, by the way, in the UK. I've never left. So I started there doing my undergraduate degree, postgraduate.
What do they call you there now? You are Professor of Particle Physics at the University of Manchester.
Yeah.
And Royal Society, as in the Royal Society of London?
Yeah.
Royal Society Professor of Public Engagement in Science.
Yeah.
So we're kindred souls across the Atlantic.
Yeah.
So, okay, so you never left. Is that because they wanted you so badly or that no one else wanted you?
Yeah, probably the latter. But I started, it was actually physics with astrophysics, my degree. So I did a degree in physics with astrophysics. Then PhD in particle physics, although the first year I was working on supernova neutrinos. So I was crossing over astroparticle physics, as we would call it. Then I got into particle physics, went to the DAISY laboratory in Hamburg and worked on electron-proton collisions, so-called diffractive scattering.
I've seen DAISY online. I've seen DAISY simulations of things. They simulate like colliding black holes and things. Fascinating. DAISY.
DESY, the Deutsche Elektronensynchrotron.
Yeah, they have a public-facing platform.
See, I didn't know that.
Yes,
I didn't know.
Yeah.
Because the accelerator is no longer operational there.
Okay.
So but it's a huge lab in Hamburg.
Mm-hmm.
So I did my PhD there. That's in particle physics. Then moved to Fermilab in Chicago for a while. And then to CERN when we were building a Large Hadron Collider. And then, but I've always...
CERN, Switzerland, yes.
In Geneva.
And remind me, that's the European Center for Nuclear...
Research.
Yeah. Acronym, French acronymed.
Yeah, because it was founded in the 1950s. And at the time, so it was what part of the reconstruction of Europe really after the war. So it was that lab was founded, I think it was 1954, 1953.
Mm-hmm.
And so it was nuclear physics at the time. There wasn't really such a thing as particle physics, I suppose, at the time. Mm-hmm. And now it's by far the world's largest accelerator, particle physics lab.
Yeah, so, I mean, the center of mass of that whole world left the United States when we stopped funding our super collider.
The SSC in Texas, yeah. The SSC, superconducting super
collider.
Yeah.
Yeah, I would have called it a super duper collider that might have kept its funding at that point. But so Europe still leads the world in nuclear particle research.
It's a very international lab. I mean, it is the world's collider.
Mm-hmm.
So although it's based in Switzerland and France, I would say it's a world lab.
Okay, that's very diplomatic of you.
Well, it certainly is. I mean, the US have a tremendous presence there, for example.
While you're saying all this to me, you're not describing this branch of your life as a musician. So just briefly remind me of that.
Yeah, so when I was 18, traditionally you would go to university there, start a physics degree. But I didn't because I was in a band, a rock band.
I could go to college and major in physics or continue with my band.
Well, but do you have that thing like a gap year, we call it, where you say, well, I'm going to take a year off the studies before I go to college or university? And so I'd said that. I'd said, I'm going to be in this band and I'm just going to do it for a year and then I'll go and do physics. But then we got a record deal, a big record deal with A&M Records. This is in 1986, 1987. It's a long time ago. Got a big record deal. And so I came to Los Angeles and recorded an album with actually produced by Larry Klein, who was married to Joni Mitchell at the time. And so we recorded some of it in Joni Mitchell's studio in Los Angeles. And then we toured with, my first professional gig with that band was with Jimmy Page, supporting Jimmy Page. And
did you open for Jimmy Page?
Yeah, we opened for Jimmy Page and Gary Moore, who'd also been in the band, Thin Lizzy, and then Europe, the Final Countdown. So you know this song, The Final Countdown, and Carrie was a big hit here in the US. So we opened for them. Made a couple of albums. So I did that basically for 5 years.
And it charted?
Actually, no. We did big shows. It was a rock and roll band. And then I left that band, went straight back to Manchester and went to start a physics degree.
As one would do, yes.
But then in that little gap, I joined another band who then had some hit records. So a band called D-Ream. This is in the early 90s now. And they didn't have a record deal when I joined them, and they got a record deal as well. So when I was at university, I was in this band. We had a #1 hit in the UK and Australia with a song which violates the second law of thermodynamics, which you'll love, called Things Can Only Get Better, which is clearly incorrect. certainly
things can only get worse globally in the universe. Yes.
Exactly. So I had a two.
Wait, and that song, what helped it, if I remember correctly, some political candidate adopted it as their theme song.
Tony Blair. It was a
Tony Blair.
Yeah, it was Tony Blair in 1997.
It became a big election. Associated with his election.
Yeah, and came back actually into fashion because we just had a change of administration in the UK, and that song came up again, and it came up and it got quite popular again. So I did Glastonbury this year with the band.
Wait, that's that huge place.
Yeah, the big festival. Yeah,
that's any huge scene of musicians in the UK is at that location.
Well, it's probably the biggest festival in the world, I would imagine. I would guess. But it's a huge festival.
So you and Brian May.
We are the two. He did it the other way around though. He got extremely he got extremely famous and then finished his PhD
in astrophysics. Yeah. Okay. Brian May, lead guitarist of Queen. Yes. Yeah. So let's pick up some of the physics. We are both here right now in Las Vegas at a World Skeptics Conference. Yeah. We're both skeptics. I mean, any scientist is a skeptic, but the problem is when the world does weird things, who's going to put them in check? Somebody's got to show up at the scene and say, no, that's not how that works. Or no, the laws of physics prevent that. Or you've had to do this in the UK, right? There's certain resonances between the United States and the UK about how people misthink things. So what was your baptism into this world?
Well, actually, I mean, I was only interested in doing research for a long time. So as a postdoc and in that part of my career, I didn't want to know about anything else other than doing research. And that's all I did. But it was, I can't remember when it was now, but there was one of those regular funding crises, as you'll know from here in the US, when government support, in particular for research, dipped. And so I got involved in trying to fight that. And we realized, I mean, it's kind of obvious, I suppose, but we realized that one of the reasons, talking to government, that they had cut the research budget was that they didn't think anyone cared. So they thought it was a simple thing to
democracy.
Do. You could just, and so we all, as a community, we were we learned again. We've learned it over the years, but we learned again that popular support for what we do is important. And where does the support come from? It comes from understanding. And there are many reasons, by the way, why talking to people who are not in science about what we are doing as scientists is important. One of them, of course, is just purely democratizing knowledge. We taxpayers fund, at least in part, what we do, and therefore they have a right to know. So there's that level. But on the other level, which I think you're suggesting as well, what science does, I think it's not about knowing the facts. Like it's not about knowing the universe is 13.8 billion years old, for example, or it's 13.8 billion years since the Big Bang. We could talk about that later, actually. Does that mean it had a finite origin in time in the past? Anyway, but it's not.
We'll put a pin in that. We'll get back to that, okay?
It's not about knowing facts so much as understanding something about the process by which we acquire reliable knowledge about the world. And science is the process by which we acquire reliable knowledge. And so I think that
it may be unique
realized
in that.
Well, in the sense that nature is there, whether the job of the scientist is to find out how it works. And it, of course, as Richard Feynman and many others have famously said, it doesn't care who you are or what your opinion is or how popular you are or how many votes you got or anything, how much money you've got. It just doesn't care. So in that sense, I think it is a unique pursuit because the standard by which your opinion is judged is external to us. It's nothing to do with humanity.
Nature is the ultimate judge, jury, and executioner.
Yeah. So I think I became involved initially just on that very narrow idea that we wanted to make sure that people understood what we did and what the value of it is. And then that branched, that became bigger and bigger in my career and branched out into television and live shows and all sorts of things. But it came from that. I wasn't interested in communicating science. I was just interested in doing it for a very long time.
So you had a certain duty and responsibility to the world.
Well, I think we all do. I mean, I've realized since that I think actually Feynman again said it's a very brilliant essay that anyone can download from 1955, I think it is, called The Value of Science. It's just 4 pages and it's there. It's on Caltech's archive, I think. And in there, he says that it is our duty as scientists, our duty, knowing the great value of, he defines science as a satisfactory philosophy of ignorance, which is a beautiful, just merely satisfactory. It's a philosophy of ignorance. You start out from not knowing. And he said the great value of the satisfactory philosophy of ignorance, the great value of freedom of thought, to proclaim that freedom and to try to protect it for all coming generations, he essentially says at the end. So, but I like the framing. It is our duty as scientists to do that, as well as do our job, which is to find things out about nature,
about the natural world. And I, in this conference, I am to bestow upon you the Richard Dawkins Award for Science and Reason. Bestow, yes. The Richard Dawkins Award is something I won last year, and I was called back in to bestow it upon you.
Passing a torch. It's a great honor.
It will be a delight for me. It takes place tonight.
Yeah.
I look forward to that. And just the idea that science and reason is something, maybe it's sad that it's something that needs to be rewarded, because if it's one of these awards that if the world functioned just right, you wouldn't need it.
And also, although I said, as Feynman has said, it's in a sense our duty as scientists. It is also true that not all scientists want to do that or feel comfortable with it. As I said, I didn't want to do it initially. Now I very much enjoy it and think it's very important. But so we don't need everybody to do it, but some people will, and that's important.
Right. So let's talk physics. Take me to the frontier of particle physics today. What's going on at CERN now that the Higgs boson is discovered and the Nobel Prizes were granted? What are they doing now?
Well,
did they just close shop and go home?
No. I mean, what particle physics is, because we're talking about quantum mechanics, basically, it's statistical in the sense that you collide. What we do there is collide protons together at high energy, and we collide a lot of protons together at high energy.
Protons have a charge so that you can put them in a magnetic field and accelerate them to very high speeds.
Yeah, so they go around. So the LHC in kilometers is 27 kilometers, and that's the number I was
circumference.
Yes, that's about 16 miles or something like that.
Mm-hmm.
And the protons go around that ring 11,000 times a second. So that's how fast they go.
That's fast.
So that's 99.999999% the speed of light.
Okay, so you've granted them energy so that when you collide them, you break them apart. You're basically deconstructing nature to see what residue comes out of it. When I think of doing that for anything else, it's going to break, right? I don't take chairs and slam them together and still have chairs. I have a pile of kindling, okay? So who ever thought it was a good idea to smash nature into itself?
Well, I suppose Ernest Rutherford initially. So we go back to Manchester, the turn of the 20th century, and Rutherford was using radioactive decay to essentially produce the particles. I mean, it's just the decay of atomic nuclei that naturally happens to produce high energy particles, which he then fired into gold foil and bounced them off the foil. In doing that, he discovered the atomic nucleus. So one way to think about particle physics is that when you collide things together, what are you doing? You're really building a microscope. One way to think of it is that the higher the energy of the collision, the faster these things are traveling, the smaller the objects you can see. So we were talking about seeing for the first time in those experiments the atomic nucleus. You move forward to ultimately through the 50s and 60s, and we have higher and higher energy collisions, you start seeing that the nucleus is made of protons and neutrons. And then you start seeing it in the 50s and 60s that the protons and neutrons are made of smaller things called quarks. And so we discover those. We've not discovered anything smaller than that, by the way.
Is it because you don't have enough energy to bust up a quark?
Yes. Or to resolve what's inside it, let's say, to build a microscope.
Because right now, the inventory of fundamental particles includes quarks.
Yeah.
So somebody saying that's fundamental, which sounds a little like the Greeks saying atoms are fundamental.
Oh, no, well, they won't be fundamental. You're absolutely right. But they look point-like from the point of view, from the energies that we can generate today. But that's one side of particle physics. So we've been exploring the structure of matter, which is historically, it goes back to Rutherford, I suppose.
And again, you have confidence that when you break matter apart, you didn't break the matter. You're just deconstructing it.
Yeah, it really, I think the way to think about it, you think about what a collision is. So let's say you collide, as we did in my PhD, electrons and protons together. So you get an electron beam and a proton beam, and you smash them into each other. What's actually happening? What's actually happening is one way that the collision can happen is that the electron can emit a photon, which is a particle of light. And the particle of light goes and it hits the proton. Now, the wavelength of that light, which is telling you how small a thing you can see, is proportional to the energy of the thing. That's how hard we're smashing the things together. So the faster you smash them together, the faster you smash together, the higher the energy, the smaller the wavelength. So the smaller the things that you can see. So that's a way of thinking about particle collisions. So it really is a microscope in that sense. Okay. That analogy works.
I'm just thinking, if I were a proton, I wouldn't want to be busted apart into quarks. That would not be a nice day for me.
In some ways, I suppose it's kind of like having an X-ray, I suppose, isn't it? You're right, though. You hit them hard enough and they fall to bits, but that would be the same for you. But we would try not to hit you that hard.
The bits that I fell into, no one's considered them fundamental bits of Neil. Right.
But the other way to think about particle physics, which is, I think, so you say the Higgs particle you mentioned. So that's not in the proton. You're not smashing the things together and finding a Higgs particle buried in there somewhere. The other side is really, so you think about Einstein's famous equation, E equals mc squared. So energy and mass are interchangeable, let's put it like that. So it also says that if we have loads of energy in these collisions, then we can make new particles that are extremely massive, much more massive.
That would come spontaneously out of the available energy that would otherwise be doing nothing.
Yeah, so we have, when you collide protons together at these energies, you have plenty of energy there to make a Higgs particle, for example, or a top quark, which is a very heavy particle as well, far more massive than the protons. So that's, I suppose, the way to think about trying to manufacture Higgs particles. So you can observe them. You need enough energy to make them.
So you're not just busting them apart. You're creating an opportunity to view more massive particles than would otherwise be available to you.
Yeah. And the other thing to say, so to get a complete picture, is these very massive things like Higgs particles, they have a very short lifetime. So you make them and they decay away into lighter particles very, very fast. So you don't see the Higgs particle. What you see are the debris from the decay of the Higgs particle. And the challenge of particle physics is to detect all those bits that came off, basically. And by the way, you also have the bits of the protons that all got smashed up as well. So it's a big mess. And we have more than...
I've seen these.
It's very hard because you don't only have one proton collision per... We send the particles around in little bunches, basically. So you can get 10, 20, 30 collisions at the same time. Only one of them, on a very good day, will be an interesting one. And then, so you've got to sift through all this, which is the difficulty or the professional challenge, let's say, of particle physics.
With that reasoning, there's always some next energy level that you haven't visited.
Yes.
Where more and interesting physics can reveal itself.
And this is where it gets challenging at the moment, because the so-called standard model Higgs particle, and I should just say for a minute, that thing, the existence of this thing was predicted in the 1960s by Peter Higgs and others. And it was a suggestion, a theory, a guess, let's say at the time, mathematically motivated, almost purely, by the way, mathematically motivated, of how things get mass in the universe at the most fundamental level. So how the quarks and these these very heavy things called the W and Z bosons, that how those things got mass. And so it was a mathematical construct. It predicted that there should be, in the simplest case, this thing, the Higgs boson, but there could be more complicated versions. And so we knew that if we collided protons together at the energies that we generate at the Large Hadron Collider, then we would either discover the Higgs boson and prove this theory to be correct, or we knew that if it wasn't there, we would see something else. So we had a very clear idea from experiment and theory that we were going to discover something with that machine. And you don't know what it is. It turned out it was the simplest thing. Mm-hmm. It was this thing that Peter Higgs had dreamt of all those years ago, which is astonishing, by the way, 50 years after the prediction. And there's a great essay that you might know by Eugene Wigner called The Unreasonable Effectiveness of Mathematics in Physical Sciences.
Yeah.
I think that's one of the best examples. It's an astonishing achievement that we got it right. And so we discovered the Higgs boson.
To put precision on that Wigner's the point in that paper, it's not that math in a vacuum, no pun intended, makes discoveries. It's the mathematical representation of a physical idea.
Yeah.
And then you pursue the math and it applies to the universe, but only if the physical idea has captured reality in some fundamental way.
Although it was, I think, it was a very mathematical framework which became the standard model of particle physics, based on ideas of symmetries and all sorts of beautiful ideas, which really did have mathematical foundations. So there's an aesthetic sense, I think, built into that model.
And that would be the pure mathematical. See, my people in astrophysics, we have enough embarrassing historical examples of chasing elegance and beauty.
Kepler. I think the genius of Kepler was that he had these Platonic solids and these ideas.
Right, he's got the pyramid and the cube and the this and
but then he rejected it based on data.
Yes,
in 16.
But his first thought was the universe is beautiful and divine and perfect, and the solids are perfect. Planets are in the universe, so it must be a connection. Yeah, he spent 10 years looking at it.
Yeah, but then
he rejected it.
And then the laws of planetary motion, which are indicative of a very beautiful thing, which is Newton's law of gravitation, an inverse square law.
Yeah.
And so there's a beauty underlying it.
But only after he had to scrap this other beauty that he had presumed it would be. That's why we step lightly when someone says, I have this beautiful idea. Yeah, okay, let's hear it.
But it is true that I think it's one of the great mysteries that there is historically, Einstein's theory of general relativity is another example where a quest for simplicity and beauty and elegance, which are judgments, right, the human judgments, has led to very, very precise models of the way that nature works.
Given that CERN, which has the Large Hadron Collider, LHC, discovered the Higgs boson, if you're going to discover more particles, presumably you have to keep sort of upgrading the system as the LHC was compared to what was there before, so that you can with ever greater force, bust into the particles and see what's lurking.
So we can't increase the energy of the LHC very easily. Or even easily, or even we can't. That would be a major change to the machine. But what we can do and are doing is so-called high luminosity upgrades, which means you collide more protons together. And the thing about
so then you win on the statistics of the
because
event.
Particle physics is a quantum mechanics, and so things happen statistically. So it's one in, I don't know the numbers off the top of my head, 1 in 10 billion collisions you'll produce something interesting. A Higgs, it's less than that. But so when giving yourself more collisions gives you more chance to discover new particles, and it gives you more particles like Higgs bosons to explore.
If you get a Higgs particle after however many collisions, and that's kind of rare, if you have more collisions, you'll get more Higgs to improve your statistics on what the hell the Higgs is.
Yeah, because we want to know.
But then there could be a reaction that's even rarer to manifest than the Higgs.
Yes.
And if your sample wasn't large enough, you would just never go there.
Yes, you wouldn't see it. If you just made one thing, one particle, whatever it is, the Higgs prime, whatever. If you made one of those, then you wouldn't see it if you made one of them.
Sounds
right?
like
you need to make hundreds.
Superhero nemesis.
Oh, by the way, and we do look for those things. The Z prime, the Z boson, we look for the Z primes because they can be signatures of extra dimensions in the universe, by the way. So we look for this stuff. But the point is that if something is very, very rare, then you won't really see it. If you just make one or two of them, you need to make hundreds or thousands or whatever it is to see them.
Yeah, it's like how many people have to live in a city before you stumble on someone who's 7 feet tall?
Yeah,
that's
so statistics.
Statistically, you need possibly millions.
Yeah. So the upgrades are the upgrades that we can do, and you have to upgrade the detectors, the cameras that we use, as well as the machine.
Okay, so you kept the same hole in the ground.
Yeah, because we don't want to dig another one of those or change all the magnets around, which are very expensive.
Does that hole go through more than one country, or is it all contained in Switzerland?
It's France and Switzerland.
Wow, okay.
Yeah, most of it's in France, actually.
Oh, didn't know that.
Only a little bit of it's in Switzerland.
Okay.
Right, good. So that's one thing. And the other thing is, this Higgs that we've discovered, the question still remains, is it the simplest one, the standard model Higgs it's called? Or is it something more complicated? How does it behave? So the analogy in planetary science would be, we discovered a moon. And so you go, great. Then you would like to know about the moon. You don't want to just say, we've discovered this moon, it's a dot. That's fine. As you said, they're interesting. You want to characterize it
in whatever way you can.
For that, you need a lot of them to observe. Mm-hmm. So it's exciting, and it's challenging because I think for the first time, it's probably true to say in particle physics, we don't know if there's anything else just around the corner, which is bad, but it's also good. I suppose it's just science. I mean, ultimately, it's neither bad nor good. It's the way nature is.
That's what triggers whatever next round of physics is complete.
Yeah.
You get those people that show up and say there's nothing left in physics to discover.
Well, they show up
every few decades.
So utterly wrong. I mean, there's tremendous progress being made. It's such an exciting time in fundamental physics at the moment. That not particle physics, not only particle physics, but we said gravitational astronomy, the exploration of the force of gravity, black holes, quantum information, which is related to quantum computing and all sorts of all that stuff is to me utterly fascinating. There's some really interesting. I read some stuff the other day, which I don't fully understand, actually. Some of the progress in string theory, it's interesting because, just as an aside, it's linking, it seems to me, it's linking one of the great mysteries, which is the so-called cosmological constant. So the fact that we observed that the universe is accelerating in its expansion.
And Nobel Prize has been given for the observation, not for the understanding. Yes.
Yeah. There's a friend of mine who, by the way, didn't believe he didn't believe it when he saw it because it wasn't in the air, this idea. He was looking at light from supernova.
Right.
Supernova.
Like I'm on a paper with Brian Schmidt.
Yeah.
I'm like a very minor author. You got to scroll down and then my name. It was analysis of high redshift supernovae.
Yeah.
And I totally enjoyed that work, but he obviously went on and made an entire sort of branch of his career on it.
So there's this remarkable idea which comes from that, which is in Einstein's theory, this idea that you can have a kind of energy in the universe, let's say, or a thing, whatever it is, because we don't know what it is, but something that makes the universe, the rate that space stretches increase, which is so that's there and it's observed. It's one of the great mysteries because I think it's the smallest number in all of physics by, what is it? It's something like a 10 to the power minus 122 or something in appropriate units, right? Which is an absolutely ridiculously, so it's a tiny, 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 tiny thing that's causing this rate of expansion. But it's not zero. And so the question becomes, why is it tiny?
Why is it tiny and not zero?
Yeah.
Right.
And so, because if it were even slightly bigger, we wouldn't be here. So the universe would have been blown apart. So it seems very unusual. But I saw the other day, actually, that there's some research that's linking that in the framework of a string theory or M theory to dark matter. So there's there's a kind of an idea that if you fix that, you get a prediction out that there should be dark matter, but it turns out it's to do with extra dimensions and gravitons in extra dimensions and things. So it's quite interesting. So I think there are some very interesting areas of string theory where progress is being made quite remarkably.
Do string theorists need a fuller or better inventory of particles? So, for example, are we still looking for a graviton? Are we still looking for, you shake a stick and there's a physicist proposing a hypothetical particle to explain dark matter, to explain whatever.
Wouldn't it be cool if the dark matter were related to gravitons, which is this is not my field. I only heard of it the other day, but it sounded interesting. But it just shows you that to go back to LHC, we have the Higgs particle, as you said. We had expected, I would say most particle physicists expected there would be other particles discovered. There's a particular
in
theory.
that same experiment.
Yeah, at LHC. So there's a particular theory which motivated by string theory a long time ago called supersymmetry, which is a property of the universe.
It's been around for many decades.
Yeah, and it came initially either from string theory or from some other physics and got incorporated in. I can't remember historically which way it came, but it essentially predicts that there are double the number of particles that we see, fundamental particles at this energy. So and they would have been great candidates for dark matter, by the way, which is an astrophysical discovery. So we should say, I suppose, the one sentence description of dark matter is that we see the universe. There's far much more matter in the universe than we can see.
See, I would put it differently.
Yeah,
I would say there's it's not dark matter, it's dark gravity.
Well,
you say matter, we don't know what it is.
Well, it's true. So you see it through its gravitational interaction.
So it's dark gravity.
Yeah.
We don't see, otherwise you get newspaper headlines say, we must abandon our ideas of dark matter. Well, if it's not matter, it's still there. Okay. It's misnamed. If we don't know what it is, we had no business calling it matter at all. But,
so the thing to say though is
call it dark gravity.
The best,
which sounds cool.
So you build models, and it is true that the best model that fits all the data, which is not just the way that that galaxies rotate and collide, and the way that galaxies kind of lens light and all those things, but also the cosmic microwave background radiation, which is the oldest light in the universe, and how that worked, and how the ripples, the sound waves went through the early universe and all that. You put it all together, and it fits if you have a light-ish particle that does not interact with light, but interacts weakly.
So this would be another category of particle in the particle soup.
Yeah. So
that has gravity, but doesn't interact electromagnetically, or only very weakly.
You can't see it.
And so it's all right.
Yeah. So that's a model, though. You're right. So that's a model, which is kind of, I would say, the baseline model.
It's the assumption. People assume that, and I don't have a problem with it. But if anything happens to that model, it gets shown it can't be true. People say, "Oh, then there is no dark matter." No, there's still dark. It is a measurement in the universe.
Yeah, I understand.
We've just misnamed it.
Yeah, I agree. The measurement is just galaxies spin round too fast.
But too fast. There it is.
Or the way they collide, and so on. There's quite a lot of independent measurements of this thing.
So tell me about graviton. I mean, is that a real particle?
I think most physicists would say that quantum mechanics
requires
is the base theory. I think the reason I'm careful is because there are some people who would say general relativity is a thing, space-time is a real thing and all that. But I think that generally most people would say quantum mechanics is underlying it. And that if you have an interaction.
In other words, quantum physics is foundational to the universe in ways that even general relativity would not be.
Yeah, so we could talk about this later, but the idea that space and time, or space-time, emerge from a quantum theory is very fashionable at the moment, partly because of the study of black holes. So we could talk about that. So given that, then I should say, just for people who are watching and listening, that so how would we picture the electromagnetic force in particle physics? So we know that if you put light charges together, they repel and so on. So what's happening there? Or if you bring magnets together, right, they repel each other. Everybody knows if the North Pole together and they repel. So what's happening? In particle physics terms, you picture that as the exchange of a photon. So it's a particle of light that goes from one particle to the other, and essentially carries the force. So that's what how a particle physicist would picture that force. All forces.
Have we successfully applied that to gravity?
No, but
give me a more resonant no.
The very strong. I suppose I'm trying to find the right word for it. I think that's why I said conviction. It's almost, I don't know of any physicist who would disagree with this statement.
You can't fold it into the quantum world, you don't really have a right to start looking for a graviton. Because you're going to say the graviton is the mediating particle.
Yeah, so it's the
in the way the photon is the mediating particle.
So, and that's, I don't think you'd find anyone who would disagree with that statement.
Okay.
Although, I don't think you would. Although, it is true to say that because gravity is so weak, so this is the other thing to say, it is tremendously weak compared to the other three forces of nature, of which electromagnetism is one.
Here's what I tell people, you've surely done this in class. They say, well, how weak is gravity? Well, I can pick something up off the floor against the wishes of Earth.
Exactly, yeah.
Yeah, the whole Earth is pulling on this ball, and I can just pick it up off and kick it into the goal.
And you're using electromagnetism. That's what's happening. So your muscles and all that thing. So this is all electromagnetic force, which completely destroys, as you said, the gravitational force.
Right.
But gravity is only additive. So it only adds up in the universe. So it is the dominant force on cosmic distance scales. That's the point about gravity.
Here's a calculation I haven't verified, but it sounded legit. Very verifiable.
Yeah.
I was too lazy. That if you take like the space shuttle in its glory days, and you remove the electrons from 1 cubic centimeter in the nose of the main tank, and take all those electrons and put it at the base of the launch pad, would not be able to launch. The attraction between the electrons at the base of the launch pad and the net positive charge at the top is enough to prevent it from launching.
Yeah, that's a cool idea.
Yeah, cool.
I could see that would be.
Actually, it would burrow a hole. So it's not a realistic experiment, but to get some sense of the forces involved.
Yeah, that's a really nice way.
Okay, so gravity's weak. That somehow bails you out of this problem?
Well, it just means that we don't have experimental access to them.
Okay.
Because it's so weak.
Whereas we do have experimental access to photons.
Yeah. Unless you could potentially have access if there were extra dimensions in the universe that are configured in the right way.
Physicists are always throwing in extra dimensions. Whenever you need it, know.
It is interesting, though, that string theory works in 10 dimensions and only 10 dimensions mathematically. So that's an interesting observation, right? So
I don't have the background to be an authentic string theory skeptic, but I know physicists who are, and so
I think there are. I mean, it depends. I think it depends what you mean by string theory. I mean, if you go back, a few decades, you talk to Brian Greene, for example, and when he started working in this area, he's
a friend of StarTalk. He's been on us several times.
He would have. And his great book, The Elegant Universe, is a beautiful description of string theory. And so I think the idea initially with the hope was that you'd have a theory and you could write it down. It's a theory of everything, and it would predict the universe as we see it.
And then you go home and you're done.
And I think that's gone as an idea. But the basic idea of these, I mean, why is it called string theory? It's because particles are not point-like. These strings are like little loops, but that idea, I think, is still at the foundation of most modern theoretical physics in this area. But it's got much more complicated, and it's been much harder. I think the initial idea that you could just predict everything from one number maybe has gone away.
One simple equation on one line.
But there is tremendous progress being made in string theory. So it's not gone away. It's just become more complicated, I would say.
Well, thanks for catching me up on this. At this conference, you're giving a talk on black holes.
Yeah.
And there was some recent announcement, the biggest jet from a black hole ever discovered, ever. When I was asked about it by the press, I simply said, there's always a biggest jet in the universe. And so now this one is that.
It's the A380.
Airbus
A380. It's a fantastic aircraft.
Did I undersell the significance of this huge jet? So what if it's the biggest one, unless there's some interesting physics that's coming out of it?
the area that I share a PhD student who's working in the area is more theoretical. It's about quantum information, the way that information behaves inside and outside a black hole, what happens to things that fall in. But in terms of the astrophysical work, if you go back, not long ago, we didn't really have any observation of how things behave in the vicinity of black holes. And so I would put it in that box. We've got several observations now. We've got the radio telescope observations from the Event Horizon collaboration that are showing us how the magnetic fields work, for example, around the black hole in the Milky Way. We've got these jets, which are giving you access to the magnetic structure, presumably, in the way that they spin.
Thank you for putting it in that context. Now I can understand. It broadens the astrophysical data set on which we can sharpen our hypotheses for what's going on.
Yeah, because they're hard things to observe.
Yeah.
And of course, you can't observe the interior because it's inside this thing called the Event Horizon. But what you can do, and we are doing, is observe the way that material behaves in the vicinity of them. Or the other remarkable thing we've been able to do in the last few years is watch them collide and see how the ripples in the fabric of the universe come out, and we can detect those ripples. So all these things are allowing us to probe these objects and it's worth remembering that they were present. They were described. Non-spinning ones were described fully by the work that Carl Schwarzschild did in 1916. So months after Einstein had published the theory of general relativity. He didn't know it at the time, but the mathematical description he found, which describes how space and time are distorted in the presence of a star, a non-spinning star, which is kind of important. Those fully describe a black hole that isn't spinning.
If I remember correctly, he would die in the First World War. I don't think he made it out of the war.
No, he died in 1916, so shortly after. Not in action. He died
was not in action. Okay.
I think he died from diseases that he was on the Russian front.
Okay.
So it was it
could be war related, but not.
Yeah, it was.
From an injury.
I think it was.
Yeah,
you would argue war related.
So we've got more than a century of mathematical foundation for this. Yeah.
And then you go forward to 60s.
With no data. No data.
No, and then so it takes another 50 years, by the way, for someone to work out what it looks like for a spinning one, which is Roy Kerr. It's a famous Kerr solution. But those two solutions are there. They're in Einstein's theory in a sense, and they describe the black hole. But observing them is something that we haven't been able to do till recently. So
and multi-wavelengths as well.
So now we have radio observations, the gravitational wave observations.
So I'll be a little kinder to that.
The thing is, as you said right at the start, science is about having ideas, building theories, and so on. But it's really fundamentally about testing those theories.
Yeah.
And so we can talk about these theoretical objects, black holes, but really, and they are rich theoretically. But ultimately, you've got to make observations. And that's where these jets and seeing how material behaves gives you access to the magnetic fields and how the thing's spinning and what it's doing. That's important.
Let's talk about your work with the public. You said earlier you share this commitment that Feynman declared, duty to bring science to the public. You not only talk the talk, you walk the walk. And you have spillage everywhere. You've given tours, public tours in Australia, across Europe. And if I remember correctly, you're coming back to the United States next spring to give a tour across the country?
Yeah. It's a tour that's been going on for quite a long time. It wasn't meant to really, but we've ended up playing to over 400,000 people across the world with this tour. We have 5 trucks and 2 tour buses. It's brilliant. So I'm reliving my life as a.
So did I see a version of that when you came to the city?
Yeah, it was very early on. Just after it was just after.
Yeah, you have these screens that interlock.
Yeah,
and then the whole stage is.
Yeah, and that was a very early iteration of this, and so it's changed a lot. Before I laid it to rest, this tour, and develop another one, I wanted to bring it back here. In the form that it is now, which is so radically different from what it was.
And it's you celebrating the universe with and for the public.
It also morphed into, there's a version that I do with the symphony orchestra, which is great fun. So I did it at Sydney Opera House actually initially last year. And it's a big orchestra because it's 90-piece symphony orchestra because of the music that I chose. And so the reason, by the way, that as a slight digression, it's part of this tour. The classical music is a big part of the tour. So it starts with Sibelius's Fifth Symphony, the third movement. And that was because a conductor friend of mine called Daniel Harding, I said to him, what should Stanley Kubrick have used in 2001 as a joke? Like, what should he have used? He immediately said Sibelius' Fifth Symphony. And it was written in 1915, same year that General Relativity was published. But it's the basis of almost every science fiction theme you've ever heard. Right? You'll hear everything in it. It's beautiful. Okay. So the idea, which I've always strongly believed, but it came to my mind as I was doing this tour, is that what if we're talking about deeper philosophical questions, which are raised by cosmology, I say right at the start, what does it mean to live a finite, fragile life in an infinite, eternal universe? Right? Is it because it? And I say, of course, I don't know the answer to that.
Does that uplift people or depress them?
Well, but it's that, as you know, the moment you contemplate the scale of the universe, and I should say, we don't know whether it's infinite, we don't know whether it's eternal, right? But it could well be infinite and eternal. For all purposes, it kind of is, right? On a human scale,
relative to a human scale, yeah.
So immediately when you contemplate the size and scale of the universe, you ask questions about our place, and quite vividly, what does it mean to live these little finite, fragile lives? And so I think I try to approach those questions, and you realize, or I realize, that there are other lights you can shine on that problem. And science is a necessary, bright and vivid light that casts a very well delineated shadow, which is giving us some, obviously it's the framework within which we operate. But there are other lights. So you realize that Mahler, for example, so we use Mahler in the classical concerts. Mahler thought a lot about what it means to live a finite, fragile life. And he gave a very eloquent answer, many eloquent answers in his symphonies. And he was once asked, by the way, what are you trying to say? What's this answer? And he said, well, if I could say it, I wouldn't have written the music.
Good answer.
So you have this music.
I love that.
So the music, so the composers that I chose, and that they are in the tour that we're going to do this coming year, next April, 2025. They're in there as music. The composers were chosen because they explored this question and gave very eloquent answers. So it adds to, I think, the more philosophical exploration of the questions that are raised by the science.
What's the name of the tour?
Called Horizons.
Horizons. That's easy enough to remember. Okay, very cool.
But there's a lot of black holes in it as well, I should say. And so it's an exploration of the ideas that I find interesting.
Black holes are a horizon of its own.
They have horizons,
yes.
Okay. But also life in the universe, the origin, evolution of life, speculations on, we could talk about it, speculations on how many civilizations there might be as a guess.
Well, this thing about life in the universe, you've done many TV series, and most recently one on the solar system.
Yeah.
Where the search for life is a main theme.
Well, yeah, we just saw, as we speak, last week, the Europa Clipper spacecraft was launched.
Yes.
On the way to Europa.
We have an entire show devoted just to that. We visited the Jet Propulsion Labs and felt the excitement of everyone there.
It's great, isn't it? It's the first spacecraft I've seen, major spacecraft being built. So I saw the Clipper. And the thing is, the scale of that thing, it's the largest spacecraft, isn't it, that's ever been sent into the outer solar system.
If you add the
most massive, I think.
It may be, but there's another important fact. Solar panels have gotten more efficient. In the day, back if you were going to explore beyond the asteroid belt, you couldn't use solar panels because the intensity of the sun wasn't high enough. This one has a very deployable, large solar panel that'll help it along without having to rely entirely on the nuclear decay of plutonium.
Yeah, so it's a huge spacecraft.
Yes.
And the point is that Europa, Jupiter's moon, is a prime candidate for a habitable world. In the, what we know, almost certainly, I'm always, the people who I know who work on the mission say, don't say we know, we're almost sure there's a saltwater ocean below the surface. I think it's pretty indisputable now, so we're pretty sure it's there.
Yeah, but whatever is the skepticism, what would it be were it not a global ocean?
Yeah, it's very difficult to be because, and that's from many measurements.
Was it made of ammonia? I mean, there's not, water molecule is not rare.
Yeah. So it looks like salt water.
And we have a lot of comparative planetology with, is it the Arctic, when it freezes over, you have these chunks of ice that will break and refreeze and readjust, and you can compare the images, and you'd think you were looking at the frozen Arctic.
Yeah. So it looks, and there's more water in that ocean than all the oceans of the Earth combined, geologically active. There are questions about how the ice cracks and moves on the surface. So it's a fascinating mission. So that's Europa. Mm-hmm. Mars, of course, which you've probably spoken about many times on this podcast. Enceladus is another one, Saturn's moon. Even out to Pluto. I mean, even
Enceladus is the ones we see the plumes, geysers, I guess.
Yeah.
When at the right sun angle, you can see. Who took those pictures? That must have been Cassini. Right.
Yeah.
So,
and also there's some measurements from Cassini, the particles in those jets of water, which are consistent with hydrothermal vent activity on the floors. And hydrothermal vents are one of the plausible candidates for the origin of life on Earth.
Yes.
So you seem to have everything. The one thing I think Europa's got that arguably nowhere else has is it looks like that ocean has been there for many billions of years. That's the baseline scenario.
And we evolved life in less time than that here on Earth.
Yeah.
Out of our
it was
oceans.
Present, 3.8 billion years ago?
3.8-ish, yeah.
And the Earth's 4.5 billion years old. So,
right.
Yeah, so it looks like you have a habitat that's been stable there. And I think that you can't claim that with anyone else.
In fact, it was taught that it took about 500 million years on Earth to get life going. But we were able to revise that number down because in the early Earth, these periods of heavy bombardment, it's not fair to start the clock while we're still getting slammed by, still accreting leftover rocks from the solar system as the temperature of the surface of the Earth is high enough to prevent complex molecules. Give us a chance, please. Yeah. So the periods of bombardment subside, Earth's surface cools, now start the clock. And then it's about 100 million years.
Yeah. So
it's like that.
Which is one of the reasons I think if you speak to many biologists, they would say that might suggest that given the right conditions, then whatever the origin of life is, there's a reasonable probability given the right conditions because it happened quickly here.
Right.
So, but that's not definitive in any sense.
But it's certainly tempting to go there.
But then, but what I find very interesting then is though, when you ask, okay, but when did life get more complex than a single cell? You're then, I don't think there's any evidence in the fossil record back beyond about 600 million years ago.
It took a while.
Of anything.
Yeah, we languished as single-celled creatures.
3 billion years plus, but it seems.
So I think people who think about this problem are honest about that. And so in the search for life on other planets, we're really looking for single-celled organisms.
Well, it would be remarkable to see anything more complex.
Yeah.
Well, it would be remarkable to see a single cell, especially if it were biologically different. So you can really show that it's got a different origin. Because it's worth saying that on Mars, the material is exchanged between Earth and Mars. So it's not obvious that you couldn't.
And you make all these points in your series.
Yeah.
Right. So where can people find your series? It's streaming, I presume.
Yeah. We've got the new one is just on at the moment, actually.
That's what I'm saying.
So the solar system. So that will appear on Apple, I suppose, at some point, and other places. Yeah. Okay. I mean, at the moment, it's on the BBC. So and it's streaming on the BBC, and then it will head off around the world. One of the coolest things I think about Europa is that the habitat, the potential habitat, requires Jupiter because of the heating. It's liquid because of it's orbiting around a big planet. Mm-hmm. But it also seems to require the other moons, Io and Ganymede, to keep it in this orbital resonance, which keeps feeding the energy in from the gravitational field. Yes. But it also might need the material from the volcanoes of Io on the surface of Europa, because they might provide the what we call the oxidant, right? So life is. So
you're saying that an Io, which is badly stressed,
it's just one big volcano.
There's one big volcano, so it spews volcanic substance. Faster than escape velocity, apparently, and then which lands on Europa, and it goes into pathways that intersect other moons, Europa included.
Yeah,
and you do this for 1 billion years,
and then the chemistry, and then it gets irradiated.
It helps out the chemistry.
Yeah, so one of the theories that I've spoken to people who are on the Clipper mission said is that that's part of the battery of life, that chemistry. So life, I can't remember who said it, but he said life. Someone said it's an electron looking for a place to land. That's what life is. So it's just in one way you can see life as electrons moving around But that means you need the chemistry to
Is that all we are? Just electrons looking for a place to land?
Well, that's what
All
a description.
I'd rather be dust in the wind.
But I find that wonderful because then you've got this habitat, which is a system. And as you said, comparative planetology you mentioned earlier, it's also true of Earth, isn't it? You can't understand Earth without understanding the system, the solar system. You need to understand the moon and how it stabilizes the spin axis, and you need to understand, of course, the sun and the way it interacts with Earth and so on.
I'm a few years your senior. I don't know if you would remember this, but I definitely do. The era where no one was thinking or caring about moons.
Yeah.
In the solar system.
Yeah.
You know, we have a dead moon orbiting us, oddly large, but fine. Let's go look at the planets.
Yeah.
And so every mission out to the planets, they looked over their shoulder and found moons which had way more geologic diversity than anything we're finding on the planet.
You know, I found it interesting because
when you were in school, where were we
pre-Voyager? Well, Voyager. So
see, I'm pre-Voyager, and Voyager turned the moons into worlds.
Yeah.
That's what happened.
Yeah.
Yeah.
So the idea you have a habitable zone in a solar system, which is the zone within which, if you have a rocky planet orbiting and everything's right, and the atmosphere is right, you could have the conditions to support life on the surface.
Well,
liquid water
on
the surface, let's say.
Right.
And so.
But that turned out to be needlessly limiting.
Well, exactly.
Yeah.
So you just say, well, Mars, Earth, Venus in our solar system.
That's it.
But then you find the habitable zones around gas giants. That, as you said, that was the great discovery of Voyager, I would say.
Yeah, it began with Voyager, really, for sure.
Yeah. It should be early 1980s, right?
So I'm delighted, even as a particle physicist, you get to also platform the solar system because you have the name recognition.
I was always, but that's why I said I started with astrophysics. I really just wanted to be an astronomer.
I
ended up in particle physics. It was almost, so I was doing astrophysics. That's what I was doing. And I thought, I want to be an astronomer. University of Manchester has the Jodrell Bank radio telescope, for example, which is one of the big radio telescopes in the world still. And so
that wasn't the one that discovered the first pulsar, was it?
No, that was Cambridge.
That was
Cambridge.
Okay.
Yeah, Jocelyn Bell.
Jodrell Bell discovered something else. I mean, Jodrell Bank.
It was one of the first, so it's one of the pioneering. It does a lot of the work on the Crab pulsar and so on. Okay. But it was. So I thought I'd be an astronomer, and I have a telescope. You know, that's what I do. I sit there and
you're
look
in the
at my
club.
telescope.
We'll accept you in the club, even though you drifted to particle physics
and space exploration. So that's what. But it was at university. I just got interested in mathematics. I didn't think I was very good at mathematics at school, and but I found out with a bit of practice, then I enjoyed it. So I ended up really getting more into theoretical physics and went that way. So that's why I ended up in particle physics, really. But then now, of course, I've every opportunity I get, I seem to drift back
because the universe is cool.
And black holes.
I want to brag about the universe, but
and black holes actually are where they intersect. They absolutely particle physics and general relativity, astronomy,
and the Big Bang itself, of course.
Yeah.
With your particle physics hat, where are we with neutrinos now? I thought they're sort of fully understood. We solved the neutrino problem in the sun. A Nobel Prize was given for that. Is there anything left to discover about this elusive particle that belongs in the I would say tree of life, in the particle tree of life?
Yeah, I mean there are neutrinos are fascinating things. They're very, very, very. They're almost massless, but not quite.
And that matters.
That should ring bells. You know, it's like why. That's the thing about science, isn't it? You go, well, why is this unusually light? Or maybe it isn't. Maybe the other things are unusually heavy, but it's telling us something.
And it's only neutrinos that how hard it is to interact with them that gives me any belief at all in some other set of particles that might exist that we don't interact with, because neutrinos are our own species.
Well, they interact through the weak force. So they'll interact
but
through
that's us. That's our little world here, right? Yeah. Any other symmetric particles, there are other forces that mediate them. Is that correct?
There would be. So if you have extensions to the standard model of particle physics, then you can have forces that change things into other things, and so different forces. But as far as we know, the zoo that we have discovered is described by the three forces: the strong nuclear force, the weak nuclear force, electromagnetism, and then hanging out there, as we've discussed, is gravity in really a different framework at the moment.
So I corralled Steve Weinberg in the elevator one day, and physicist. I'm telling the audience. Particle physicist.
One of the greats.
Yeah, and he went to my high school.
Did he?
Allow me to add,
Yeah,
one of
Nobel
our
Prize winner,
one of our 8
model.
Nobel laureates from my high school. And I said, how can you live with yourself at night, given how many particles there are? Come on, there's I lost count. What does this mean about our universe? And he said, it's not how many particles there are. It's how many laws we have that describe them all.
Yeah.
And it's only just a few.
Yeah.
I thought, damn, good answer.
I remember Stephen Weinberg.
Good answer.
I think I'm right in quoting him as saying that he almost wished black holes didn't exist because they're so perplexing that it would be just easier. And he was kind of joking, of course, because physicists love a mystery. But he was almost like, this is too difficult. They're too bizarre. Maybe nature doesn't make them.
Oh, I got it. So he's invoking human limitations on the capacity of nature.
Well, he was kind of joking. He was just saying these things are so baffling and so weird. Mm-hmm. In some ways, I'd rather they weren't there. You know?
Did he say that in his old age so that he was getting tired of solving the universe?
He was joking.
So we're still trying to explore neutrinos. And as I understand, there's a new neutrino experiment that just came online.
I mean, there are several. I mean, what the fundamental question, they do seem, the reason we're interested in them, we're interested in them because they're 3 of the 12 fundamental particles, right? So we are made of basically 3 particles. That's us. And
the electron, protons, neutrons.
Well, no. So the protons and neutrons are made of quarks.
Oh, so okay.
So up quarks, down quarks.
Let's start from the Greek. We're made of atoms.
You can start with we're made of atoms, and what are atoms made of?
In Greek, means indivisible.
Yeah.
That's what that word means.
Yeah, and it is remarkable, by the way. You say the Greeks 2,000 years ago, we only discovered the structure of atoms in the 20th century.
Or that atoms existed.
Well, yeah, it was up for debate. The turn of the 20th century, it was one of the debates in science. Is there such a thing as an atom?
Yeah.
It's incredible.
Incredible, yeah.
And Einstein, indeed, in 1905, one of his famous papers was on Brownian motion, which one of the 3 famous papers in that year. The other one was special relativity, and the other one, when he got the Nobel Prize for, was the photoelectric effect. So the third one. And it was
Einstein, we should just retroactively give him like a dozen Nobel Prizes.
It's astonishing.
Yeah,
he didn't get the Nobel Prize for relativity. He got it for basically the foundation to quantum mechanics.
Yeah.
We discover that matter's made of atoms. And then we very quickly discover after that the atom is electrons. Initially, we have this almost solar system-like model that it's a nucleus, a dense nucleus with an electron going around it. And then we discover the nucleus is made of protons and neutrons. That's 1930s, by the way.
That orbit model is still the symbol for an atom.
Yeah. The atomic
we kept it
energies,
just because it's classic, but atoms look nothing like that.
No.
Right.
And so then quantum mechanics comes in, tells you can't have that because charged particles moving around in the vicinity of other charged particles radiate energy away and they wouldn't be stable. And that was known, of course. And so then you find that the nucleus is made of protons and neutrons. And as I said, the neutron, it's a 1930s discovery. So we're not that long ago.
I'm amazed when so much, we're now in the centennial decade of the discovery of quantum physics back in the 1920s. And the whole 1920s was done before we discovered the neutron. That's crazy.
Yeah, it's almost living. It is living memory for some people.
Yeah. Okay, so let's get back to the fundamental particles.
Yeah.
So
then we discovered that the protons and neutrons are made of quarks.
Quarks.
So they are, as far as we can tell, point-like objects. So they're fundamental. They won't be, but as far as we can tell, they are experimentally.
So we have the photon, the electron.
Well, let's take
quarks.
The matter particles. So we have. So the up and down quarks make up protons and neutrons. So a proton is 2 ups and a down, and a neutron is 2 downs and an up.
Got it. And we have 2 quarks per energy stratum here, correct?
Well, so then we discovered. So we have this nice thing. So we have the electron, as you said, the up and down quark, and then the thing called the electron neutrino, which we just talked about neutrinos.
So only 4 fundamental particles in anything we know or care about.
So we have 4 of them. Yep. That's it. And then we have
I can construct you out of these particles.
Yes.
If I had the recipe.
Yes. But then, so we have 4 of them. So
Okay.
that's it. There's 4 of them, and then the forces that mediate the interactions, right?
Okay.
And which we can also think of as being carried by particles, as we said.
Okay.
We have the photon,
The massless
which does
particles.
the electromagnetic force. We have the W and Z bosons, which
Okay.
do the weak nuclear force, and the gluons,
Or
which do the strong
force.
nuclear force and stick the quarks together.
Aptly named gluon.
The gluons,
Yes.
yeah.
Okay.
And so that's it, it seems, except that there are 2 copies of those that are identical, except they're more massive. So there's the charm and strange quarks, and the muon and the mu neutrino. That's another family.
That's nothing. That's the next level up in energy.
They're more massive.
More massive.
Yeah.
Okay. Okay.
So you have the charm and strange, and the muon and the mu neutrino, and
Then
then
you have another one.
yeah, which are the bottom and top, or sometimes called beauty and truth, depending on how you want to do it. The quarks, and then the tau and the tau neutrino.
Okay.
And that's it, as far as we can tell. So those are the matter
4,
particles.
8, 12 fundamental particles, and their antimatter counterparts.
Yeah, and then the antimatter
Yeah,
counterparts.
okay.
And so why, we don't know. So why there are 3, and with experimentally proven, really, with some very small caveats, only 3 generations, only 3 families of these things.
Is there reason for there to be only 3? Could there be 5
we don't know.
or
Yeah,
10?
so we don't know.
Yeah.
It must be something to do with the underlying. So it looks like a periodic table. So remember, you go back to Mendeleev and the periodic table.
Yeah.
How do you understand that pattern in the chemical properties of the elements? You understand it when you know that everything's made of atoms.
Yeah, I mean, the chemist arranged it, but didn't have any understanding of it.
No,
Quantum physics.
Well,
Right.
you need to know the structure. You need to know that there's a nucleus, and there's hydrogen's got 1 electron, and helium's got 2, and carbon's
Alchemy only
4,
gets you
and
so far.
Yeah. So you understand chemistry. You understand the pattern when you understand the building blocks.
Okay.
So we don't know why that pattern is there, but it's clearly telling us about the building blocks or the underlying theory, which we don't know. So it's one of the great mysteries. So that's the zoo of particles as we know, and then there's the Higgs.
And just to be clear, when I attacked Steven Weinberg in the elevator, most of the particle identities I was referencing are different combinations of different quarks.
So
come together.
Yeah, so all these, like you said, in the 50s, and people were discovering all these things, and they're different combinations of ups and downs, and strange and charm, and bottom, and and so on.
Mm-hmm. So they exist in our universe, but again, they're made of the more fundamental.
Yeah. So basically, these things, the proton and neutron, they're kind of analogous to an atom in a way. So they're a thing. They're quite big things in particle physics, and they have an internal structure. And one
themselves,
of the things that I was involved in that we did back in Hamburg all those years ago was we were mapping the structure of the proton. So we're saying what is in the proton? How does it
mapping
work?
the interior structure of the proton?
And we need that. We needed that for the LHC. So we need, because we collide protons together. So we have very detailed maps, if you like. They're called structure functions, but they're maps of the proton.
Well, Brian, thank you.
Right, pleasure.
For joining me.
I always love talking to you and being on this podcast.
We're kindred spirits in this world, and I wish you great success with your spring tour. Does it go beyond the United States? Is it a world tour?
It has been a world tour. We've been to, I don't know, 20 or 30 countries. As I said, we're probably approaching 500,000 people who've come to this one.
So that's
we're at the end, really, of this one.
Oh, okay.
And so I just wanted to bring it back here. It's changed so much. We kind of started in the States, actually, with it in its proto form. And now I've loved doing it so much, and I just wanted to bring it back.
I just like the idea that a science talk is being given, but there are trucks that have to unload the staging for it.
It's proper rock and roll. I got roadies. I've got everything.
Do you have a tour T-shirt with the cities on it? Yeah.
Yep. Oh yeah.
All right.
I should have brought one to show you.
I want one of those shirts.
Yeah.
Oh my god.
Oh, we've got everything, and we've done so many shows. I don't know how many it is. 150, 200. They don't all fit on one T-shirt.
So, what was the name of the song again that you performed?
The most famous song is a song called "Things Can Only Get Better," which you will say correctly runs a counter to the second law of thermodynamics. So it's an inaccurate song, but yeah.
Yeah. Sometimes you got to break some eggs to make an omelet, as they say. All right. So, Chuck, we left off with a brilliant question about here we are in our universe that has our own horizon, and we come up with our own theories of the universe. And one of them is that there might be a multiverse. So beyond our horizon, if it's not in our universe, why should we even believe that the rules that predict a multiverse would even exist?
There you go.
Yeah, I love that.
Yeah. There's a lot to unpick there. So our horizon, first of all, there is a limit to how far we can see, which is the fact that our universe is of a finite age, or let's say there's been 13.8 billion years since the Big Bang. And so there's a finite distance you can see because light travels at a finite speed. So we are very sure that there are galaxies way beyond our horizon, but essentially the light has not had time to reach us from them. Now, actually, as Neil said in the answer to the last question, you can say, well, observationally, do we see any evidence of the laws of nature? So the strength of gravity, for example, going back to the last question, changing as we look out to the most distant galaxies? And the answer is no. We have no evidence that they change in the patch of the universe we can see. So that's the observational point. But when you start to talk about the laws of nature in different regions of the universe, or multiverse, as you said, then it becomes more interesting. One multiverse, there are lots of different kinds of multiverse, but one of them is called the inflationary multiverse. So we have a theory called eternal inflation, which essentially leads to the idea that there are perhaps an infinite number of bubble universes, of which ours is one. And the piece that we can see, the observational, the little piece we can observe, is a patch in one bubble universe amongst perhaps an infinite number of bubble universes in the inflationary multiverse. And those theories do lend themselves potentially to the laws of nature in each bubble possibly being different. And the way I sometimes picture it is like a snowstorm with snowflakes. So every snowflake is different. Because it's had a different formation history. But there's something similar about them all, which goes to the underlying structure, which is to do with the water molecule itself. So there's something similar, there's an underlying framework, but every snowflake is different. And the inflationary multiverse can be like that. So you can imagine that the laws we see, things like the strength of gravity, sort of crystallize out as these bubble universes form from the potential, which is this thing called inflation that's potentially going on all the time. So it's possible that different universes have different emergent laws, things like the strength of gravity. I think most physicists, probably all, expect that there'll be some kind of underlying framework, which could, something that we don't know what it is, right? Something like string theory or something, which underlies the whole thing. So that maybe Neil wants to add, but that's my summary of the inflationary multiverse.
I love your snowflake analogy, but suppose that do you have enough latitude in your eternal inflationary multiverse model to have a universe that has 5-pointed snowflakes instead of 6? I mean, how much room do you have to just make stuff up?
We don't know. This goes back to, it links to something called the string landscape, which Leonard Susskind actually wrote a great book called The Cosmic Landscape a while ago, detailing this theory. So when you look at string
Just
theory,
remind me, Leonard Susskind is the one who's a big exponent of the holographic universe. That's the same guy.
Yeah, he's one of he's been at the cutting edge of physics for decades, right? And so in the string landscape, the idea is that in string theory, it turns out you can have, there's a number that they calculate. I don't know how they do it actually, but it's something, well, I do know how they do it. It's something to do with all the extra dimensions being curled up and stuff. It doesn't matter. But essentially 10 to the power 500 different possibilities. So one with 500 noughts after it. These are the different ways that you can produce laws of physics like the ones we see from the underlying theory. And that was seen as a really
That's
disappointing.
a lot of wiggle room right there.
Yeah. But the way I see it, it's almost like saying we understand DNA. So in biology, we have a theory, we have these things A, C, D, T, and G, right? The 4 different bases that come together to form DNA. And it's like saying, okay, so there's an underlying theory. It's pretty simple. It's the double helix. It's chemistry. Out of that, it's like saying, right, predict a human being.
Yeah, you can't.
So of course you can't, because there are many different combinations of DNA, and we have no understanding yet of which ones would work and which ones wouldn't, and which ones can be realized by evolution and which ones can't. You know, it's just.
I mean, it's an astronomical number of combinations of just to make humans, let alone
exactly.
all forms of life.
So it's like saying we understand the basic chemistry that gives us that thing, DNA, but then from that, predicting a particular instance of that, an organism, is of course it depends on its history, it depends on all sorts of things. And it's the same.
If you look at that like, I don't know, an alphabet to create a language, can you rule out the nonsense? For instance, if you know English, you know that HLPPP5 is not a word. How do we narrow that?
Well, I mean, we don't. I mean, we don't know. We haven't got the expertise. We don't really know what the underlying theory is. But I mean, for example, you could imagine a bubble universe that forms and gravity is so strong that it just collapses again in a millisecond. There may be many universes like that. So that might be, as you say, that might be a universe that we consider was just never got going. So it might just about form and then collapse again. So I just want to emphasize, this is speculative stuff. So the string landscape, as I said, Leonard Susskind's book is great on this. And then the link, though, it's interesting that inflation, which Neil will know about as well, that's a theory that was introduced initially just to deal with something called the horizon problem. You mentioned the horizon. It's essentially the unexplained point that if you look in one direction out into the universe as far as you can, and then turn around and look in the other direction, then you're looking at points that emitted light that we're receiving now, that now in the universe is something like 93 billion, I think it is, light years away, right? Because of the expansion of the universe. So you're looking at points that in the standard model of things could never have been in contact with each other, and yet are at the same temperature. So 1 part in 100,000. Which is an observation.
Interesting.
So that means, and inflation
just a
was
quick
initially...
thing, Chuck, I think we did an explainer on this.
Yeah.
There was something where I was talking about that the universe has a more uniform temperature than different parts of the same room you're in.
Right. Well, that's because we with that explainer, we were talking about redshifting is kind of how we got into it.
Oh, that's how we got there. Because I was saying you have an air conditioner in a corner, you have a heater over there, and you're fine if it's a 5-degree range in a room that's talking to itself thermodynamically.
Yeah.
And now we have across the whole freaking universe, and it's within 100,000th of a degree, which is completely mind-boggling freaky, and we needed a freaky explanation for it.
Yeah. So inflation was the idea that once upon a time they were in contact. And then the universe expanded very, 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 very fast for probably a small amount of time, and so we thought that they couldn't have been in contact with each other, but in fact they were, and so that's why inflation was introduced. But it ended up doing several things that it was not designed to do initially. One was that the thing that drives inflation, which has got a fancy name called the inflaton field, but it doesn't matter what it is.
It's a breakdown in the supply chain.
Two points were doubling if you take the 2 points in the universe, then they double, the distance between them doubled every 10 to the minus 37 seconds in the basic models of inflation. So it's much worse than we're going through now with prices. It's an exponential expansion. But in looking at that, Stephen Hawking actually was involved in this, and many physicists in the 80s found that so that theory, it was discovered, predicted that there would be ripples in the density of particles in the universe through the Big Bang as inflation drew to a close, which are the ripples that we see in the cosmic microwave background radiation, which you may have talked about, and also actually in the distribution of galaxies across the sky. So there's a distribution. They're not just completely random across the sky. There are patterns in the galactic distribution. And that was predicted before it was observed by this theory. So the theory is interesting and textbook, right? You'll find it in cosmology textbooks. But the eternal inflation bit, which is kind of an add-on to that, ends up with this idea that inflation doesn't stop everywhere at the same time, basically. So you get multiple bubble universes. And then that theory, it was noticed that that's a mechanism to realize the string landscape, which gives you the possibility of varying the laws of nature in each of those bubbles. So that was the history. So it's not just, it sounds fantastical, but it's not just like somebody just dreamt it up one day and said this would be.
I try to make that clear because otherwise they think we're just pulling stuff out of our ass.
I'm asking myself after I watched the movie, The Atom Project, if you really can time travel with wormholes.
I presume I think everyone knows with Einstein relativity, you can travel into a future, all right, or at least into the future of where you once were. So let's confine this to, can you go backwards in time? Do wormholes enable this at all?
Wormholes are getting increasingly interesting, actually, particularly in the study of black holes. We can get onto that. But so yes, wormholes are allowed geometries in Einstein's theory of general relativity. If you just take that theory alone, what do I mean by that? So they really are shortcuts through space and time. So you can imagine, traveling from New York to Sydney. It takes a long time. You go around the surface of the Earth, or you could tunnel through, and you could get there quicker. So yes, if wormholes exist, and you could travel through them, and they were big enough and stable enough, then you can build a time machine. Now, virtually every physicist who works on this, and Kip Thorne, actually, who got the Nobel Prize for gravitational waves, did quite a lot of interesting work on this. It looks like...
And he was a main advisor in the movie Interstellar.
He was, yeah.
In fact, an executive producer.
And
the robot in that movie was named Kip.
It was, and it has a wormhole.
That. Yeah.
So, and he also actually suggested to Carl Sagan in Contact that wormholes were used in the film,
in the movie Contact,
and the book, and the novel actually first. So, when you add quantum mechanics into the mix, which is the theory of everything else, because our universe hasn't just got gravity in it; it's got all sorts of other things in it as well. Obviously, atoms and electromagnetic radiation and so on. Then it seems like the wormholes are inherently unstable, the big ones. And if you try to travel through one, it collapses. So that's basic. I should say, by the way, that they're such an integral part of Einstein's theory. There's a very famous paper in the 1930s by Einstein and Rosen, and they were called Einstein-Rosen bridges before they were wormholes. And they're built into the basic description of a black hole. If the black hole had lived forever, called the maximally extended Schwarzschild metric, right? Whatever it's called. But it was that which was discovered by Schwarzschild in 1916, just after the theory was published. Then there's a wormhole in there, right? So they're just fundamental to the theory. But most physicists believe, and Stephen Hawking wrote a paper actually called the chronology protection conjecture, where he thought about this. But these things would not be stable, and you can't travel through them, so you can't build time machines. However, it's worth saying that wormholes are becoming very, very fashionable now in what's called the ER equals EPR paradigm. So Einstein-Rosen, ER is Einstein-Rosen, this thing from the 1930s where Einstein and Rosen noticed that these geometries exist in space-time, or can exist. EPR is Einstein-Podolsky and Rosen, spooky action at a distance. It's quantum entanglement. And so what now is very fashionable and looks... it's one of the best explanations of how information gets out of a black hole, is that this plays a role. So there's a kind of a dual description. So we've got quantum entanglement, which is this spooky action at a distance thing, where you separate things to large distances and they're still linked in some way. The linked in some way is starting to look possibly like you can describe that in terms of wormholes, microscopic wormholes linking them together. But this is stuff that's being done now, 2020, 2022. So it's on the edge, but people are taking it very seriously.
So Brian, how do you use wormholes to actually travel backwards in time? Is that possible?
Well, so yeah, if they were stable, or you could stabilize them in some way, then you could use them as time machines, and that's considered to be unlikely. But it really is true to say that it's very true to say we don't have what's called a quantum theory of gravity. So we don't really, in any sense, understand the deep merger between relativity and quantum mechanics, which you need to understand to answer that question. Many physicists point out that we don't, it feels like it's no way to build a universe. We've all seen Back to the Future. We all know the paradoxes that happen if time travel is a reality. So I think if you pushed most physicists and said, don't be formal about it and don't say what I just said, which is we don't understand quantum gravity yet, then most physicists would say, okay, we think the laws of nature will be such that there aren't stable, macroscopic, big wormholes. That's what I think most physicists would say. But actually, you mentioned Interstellar, and Kip Thorne is one of the world experts on this, does point out that you can get around this. So you could have a universe which permitted time travel and was not full of contradictions if there were no free will at all. So the whole universe itself is completely consistent, and the time travel is built into the consistency. So that's actually what you see in Interstellar. So that happens in the plot of Interstellar. He can't stop it. I'm not spoilers, but he can't stop himself leaving his daughter's room in the past.
And by the way, that's also what happened in the story Slaughterhouse-Five by Kurt Vonnegut, which is a time travel story on top of being a World War II story. But I think Kurt Vonnegut got it right. Correct me if I'm wrong, Brian. He just described your life is always there. You're always being born. You're always dying. You're always in school. You're always in love. And you just rejoin where you were on that timeline and relive that.
There's a Stephen Hawking's birthday party. No, it's Kip Thorne's birthday party. There's a proceedings. So Neil, when we go to scientific conferences, you have a proceedings. It's a big thing. And there's a proceedings for one. I think it's Kip's. I think it's his 60th birthday party. And Stephen Hawking gave a talk, and it's written up in the proceedings of his birthday party because he's so eminent. And Stephen said that Kip has become increasingly interested in time travel through wormholes as he's got older.
Chuck, this is our third of three segments. Give me a few. See if you can slip in a few more questions.
All right, here we go. This is Catherine Cellarini Moore, who says, Dr. Tyson, Dr. Cox, Lord Nice, hoping that you can hear Dr. Cox elaborate on he alluded to in his YouTube video regarding time and space not being the stuff from which everything else is derived. Rather, that time and space may be derivative of something much bigger, much deeper.
Or deeper.
This comes from the study of black holes primarily, and I would say it looks like space and time emerge from quantum entanglement. So we mentioned entanglement before. I should say what it is, by the way. Shall I say what it is? Shall I give the 1 minute introduction to entanglement?
Sure.
So imagine you have a coin and you can toss it and it can come up heads and tails. If it was a quantum coin and there's two of them, they can be in what we call a state such that you could separate these coins out across the Milky Way to the edges of the universe. And you just look at one of them and you could toss it and it would be heads and tails. So you can look at it and it's heads, you look at it again, it's tails. 50% of the time looks completely normal. But actually, if you got back together after doing lots of experiments on this thing, you would find that the coins never came up heads at the same time or tails at the same time. They're always heads, tails, plus tails, heads. Or heads, tails, or tails, heads, right? They're always opposite. So you can build a quantum state like that. That's called entanglement. So it's an interesting thing. It's kind of, it's like the information, all the information contained in this system of two coins is somehow spread between them, and they don't behave as individual entities, even if you separate them to vast distances. So that's entanglement.
Because they're not just coins, they're also waves, and the waves know about each other outside of the local place where the coin is getting flipped?
No, it's.
If that's the truth, then I've been saying it wrong all these years.
No, they really are. The best way to consider it is it's a single system, and the information, the structure of the system is a property of the whole thing.
Why isn't that the wave function?
That's the best way to think about it.
That's got to be the wave function.
Oh, it is the way. Yeah. So
that's what I'm saying. That's what I'm trying to say. Okay.
The wave function, you'd write it down. It'd be heads, tails plus tails, heads. Is an example of a wave function, and for the geeks there, we can have a 1/√2 there in front of each one if we want equal probability.
You've gone too far, Brian.
Anyway, so that's an entangled system. And
deep in there is that there's a term that's squared in the wave function, so he's got to put the square root of 2, so that when you square that, it becomes a half.
Yeah, if I want the 50-50 thing.
Yeah, that was a missing piece of what he was saying there.
Yeah,
okay.
It's the amplitude, right? So that's entanglement. It's a fundamentally quantum mechanical thing, and it's very well understood, and we use it in technology and quantum cryptography and so on. So it's a thing. This is how the universe works. And it does seem as if, as I mentioned before, the idea that you can also interpret that as having wormholes connecting these things together.
I love it.
Essentially, what you're seeing is that entanglement and space are intimately related. That's the modern way of looking at this, the very modern way. And I think it's fair to say that most physicists would say that the entanglement is the fundamental thing. And so we're beginning to think now that you have a theory of quantum mechanics, quantum field theories, on some surface or something, and then the entanglement actually it produces the space. I mean, it's true to say that entanglement, I've seen it said, which is a beautiful thing to say, that entanglement is sort of the glue that keeps space together. And so entanglement is fundamentally related to space, and therefore time, but it's more obscure.
So that's the next sci-fi frontier, because the latest Doctor Strange is madness through the multiverse or something. So they got the multiverse in there, and he's opening up portals, which are basically wormholes, as he, jiggles his hand. So now we got to somehow get down into the very fabric of the space and time itself. That would be good. All right.
Cool. Dr. Tyson, Dr. Cox, Chuck, here is there a parameter edge of the universe? And where in relation to that edge is the Earth or the Milky Way located? Are we closer or farther to the center of the universe? Also, how do we know the universe is expanding? And is it just that our instruments are getting stronger?
So no, we're not at the center of the universe. We're at the center of the observable universe, because that's just a piece that we can see.
Right.
But the universe extends way beyond that horizon, and so it could be infinite in extent. We don't know. So, but it's much bigger, I think, than the piece we can see. So no, we're not at the center of the universe. It might be an infinite universe. We know it's expanding just very simply because we look at light from distant objects, and that light is stretched. And the explanation is that light is a wave, and it's traveling through expanding space. And so it gets stretched as it journeys. And what the basic observation, all the way back to Hubble, is that the further away
Hubble, the person,
Edwin
right?
Hubble,
yeah, yes,
all the way back to Edwin Hubble, the further away the thing is, the more the light is stretched when it reaches us, and that's what you would expect if space were expanding, essentially at a uniform rate. It's actually changing a bit. It's expanding a bit faster now.
Okay, so there is no. So if we said, I want to go to my horizon, Chuck, let's leave tomorrow.
Yes.
So then, what would we see?
You'd see the same universe as far as we know. So you could go to the horizon and look around, and you'd see a completely uniform universe with the same kind of distribution of galaxies.
So like a ship at sea, it's carrying its horizon with it, basically.
Yeah. So yes, that's a good example. If you go to the horizon on your boat and go to the horizon 20 miles away, whatever it is.
Right.
Yeah.
So you go to the horizon and you just see ocean. And you go to the next horizon, you just see ocean. And that's what the universe is like as far as we can tell.
We have electron microscopes to probe smaller stuff than with regular light microscopes. Do you think somebody is going to come up with a quark microscope or something of that nature that will enable us to see even smaller or get closer to those strings?
So regular microscopes use visible light, and visible light has certain wavelengths. So if you really think about it, a visible light telescope can't see anything smaller than the wavelength of light you're using, because the light would just wash over it and wouldn't be able to bring it into focus. So electron microscopes use basically, I think, Brian, is it X-rays? Because electrons and X-rays are the same thing at certain. You can beam electrons to have an energy level of that of an X-ray, and X-rays has really small wavelengths.
Yeah.
So now you can see detail way smaller than visible light. So this questioner knows this about electron microscopes and wants to take it another step. So
and there's a really great fundamental point to make here, which goes to black hole physics actually again. Is that so as you make if you take the wavelength down, quantum mechanics allows you to think of light as a wave or as a stream of particles called photons. And as you shrink the wavelength, the energy of the photon goes up. So that's just basic quantum mechanics. So the smaller the wavelength, the higher the energy. So you get to a point where if you want to probe smaller and smaller distances, what actually happens is you make a black hole, because you put so much energy into the small piece of space that a black hole forms. And then as you put more energy in, the black hole grows. And so you end up reversing that process, because as the black hole grows, then you get less and less resolution again. So there's a limit. You get to a point where if you try to cram more and more energy into a smaller and smaller amount of space, which you have to do to see the small thing, you have to get more energy in, right? The smaller wavelength.
Because you're using photons that are higher and higher energy.
Or anything, yes, or anything, electrons or whatever it is.
Yeah.
Then there comes a point where you form a black hole. Tiny black hole. Tiny. So you wouldn't notice it, except you'd stop seeing. So you can't probe smaller and smaller distances forever. I think Susskind calls it the UVIR connection, ultraviolet infrared connection. I think that's what he calls it. Okay. So, but it's a fundamental property of the universe. So black holes stop you from doing that, going to smaller and smaller and smaller and smaller distances.
Those pesky black holes.
Yes.
Yeah. And again, it's fundamental. It's pointing to fundamental physics. So we go all the way back to this idea of space and time and the link to quantum theory.
Dude, we got to wrap it up there. Oh my gosh. Did we cover the universe here? All right. This has been a delightful, I think long overdue episode with my friend and colleague and partner in crime, trying to educate the world of everything cool in the universe and especially in the world of particle physics, Brian Cox. Thank you, Brian.
Thank you.
All right. And Chuck, always good to have you, man.
Always a pleasure.
I'm Neil deGrasse Tyson, your personal astrophysicist. As always, I bid you to keep looking up.